Look up at the night sky on a clear, dark evening. You see a breathtaking tapestry of stars, planets, and the faint, silvery band of the Milky Way. It's a sight that has inspired wonder for all of human history. But what if I told you that everything you can see, every star, every galaxy, every flicker of light accounts for less than 5% of what's actually out there? The universe we observe is just the visible tip of a cosmic iceberg. The vast majority of the cosmos is made of something else entirely, something invisible and mysterious. This is the realm of hidden particles, the universe's greatest and most profound unsolved mystery. For decades, scientists have known that the motions of galaxies and the very structure of space itself can only be explained by the presence of something we cannot see. This isn't empty space, it's a universe teeming with activity just beyond our perception. Today, we are embarking on a journey to explore the cutting edge of physics, to pull back the curtain on the invisible architecture of reality. We will venture through 30 mind-bending theories that attempt to explain what this hidden cosmos is made of. This is a frontier where the familiar rules of physics break down, where our understanding of matter, energy, and existence itself is being completely rewritten. From the elusive nature of dark matter that binds galaxies together to the possibility of extra dimensions curled up smaller than an atom, the answers we are seeking could redefine our place in the cosmos. This exploration isn't just about satisfying scientific curiosity. It's a fundamental quest to understand what the universe is truly made of. You are about to discover how theoretical physicists are using immense creativity and powerful tools to probe the shadows of reality, proposing particles that pass through our bodies by the billions every second and forces that shape the universe in its first fleeting moments. Each theory is a piece of a grander puzzle, a step closer to a complete picture of the cosmos. So prepare to have your perception of reality challenged. We are about to dive deep into the quantum foam to explore the hidden particles and the astonishing theories that suggest our universe is far stranger, more complex, and more wonderful than we ever imagined. Our journey into the hidden cosmos begins with the most sought-after phantom in all of physics, a leading candidate known as WIMP. The name itself, weakly interacting massive particles, tells you almost everything you need to know about why they have been so elusive. Imagine a particle that is heavy, potentially many times heavier than a proton, yet it barely acknowledges the existence of ordinary matter. It doesn't interact with light, which is why it's perfectly dark and invisible to our telescopes. It doesn't feel the strong nuclear force that binds atomic nuclei together. Its only methods of making its presence known are through gravity, the force that sculpts galaxies and holds them together, and the weak nuclear force which is responsible for certain types of radioactive decay. This incredible shyness is precisely what makes WIMP such a perfect fit for the dark matter puzzle. They would be everywhere, forming a vast, invisible cosmic scaffold. Billions of these particles could be passing through you and the Earth itself every single second without a trace, like an endless, silent ghost rain. For over 3 decades, the hunt for these phantoms has been a primary focus of experimental physics. To have any hope of detecting such a faint whisper of an interaction, scientists have built extraordinary laboratories deep underground, shielded from the constant barrage of cosmic rays and other background noise that would drown out the signal. Places like the Sanford Underground Research Facility in South Dakota or the Gran Sasso Laboratory in Italy house incredibly sensitive detectors, often kept at temperatures near absolute zero, waiting for the once-in-a-lifetime event where a WIMP might nudge an atomic nucleus. They wait in profound silence and darkness, seeking a bump so tiny it defies belief. The pursuit has been grueling, with several tantalizing hints over the years that have ultimately faded away, leaving the fundamental nature of WIMP still shrouded in mystery. Yet, the scientific community persists because the potential payoff is nothing less than revolutionary. Catching a WIMP would be more than just identifying one new particle. It would be a direct window into the physics that govern the universe in its earliest, hottest moments. It would confirm that dark matter is a relic from the Big Bang, a frozen fossil from the birth of everything, and it would open up an entirely new chapter in the standard model of particle physics. Finding a WIMP would be like discovering a hidden continent on the map of reality, revealing a fundamental component of the cosmos that has been right beside us all along, shaping the universe from the shadows. But while the search for heavy WIMP continues, another compelling candidate has emerged from an entirely different corner of physics, born not from cosmology but from a deep puzzle within the heart of the atom. This is the action, a hypothetical particle that is almost the complete opposite of a WIMP. Where WIMP are imagined as heavy and sluggish, actions are theorized to be incredibly light, potentially billions of times lighter than an electron. And this isn't just a minor detail, it fundamentally changes their behavior. If dark matter is made of actions, it wouldn't be a sea of discrete particles, but something more like a pervasive, invisible energy field that permeates all of space, a cosmic symphony of waves oscillating throughout the universe. The origin story of the action is one of the most elegant in theoretical physics. Scientists in the 1970s were grappling with a perplexing question. Why is the strong nuclear force, the glue that holds protons and neutrons together, so perfectly symmetrical? The laws of physics as we knew them suggested it shouldn't be. The equations allowed for a type of asymmetry that would cause the neutron, a neutral particle inside every atom, to possess a tiny electric dipole moment, a sort of internal positive and negative charge separation. If this were true, it would have dramatic consequences for the universe, but incredibly sensitive experiments have shown that the neutron is perfectly symmetrical to an astonishing degree of precision. This presented a fine-tuning problem that made physicists deeply uncomfortable. To resolve this, a new mechanism was proposed, and it predicted the existence of a new particle, the action, which would naturally sweep this problematic asymmetry under the rug, restoring balance to the quantum world. It was a solution born of pure theoretical necessity, and for a long time, the action was seen as a curious byproduct of solving one problem with no connection to others. Then a brilliant realization occurred. If actions exist, they would have been produced in colossal numbers during the Big Bang, and because they interact so weakly with ordinary matter, they would never have gone away. They would still be here, flooding the cosmos, and their collective gravity would be immense. In a stunning twist, the action, invented to fix a problem in quantum mechanics, turned out to be a perfect candidate for the dark matter that governs the motion of galaxies. One of the most fascinating aspects of actions is that we might be able to create and detect them right here in our solar system. The core of our own sun, a raging nuclear furnace, should be a prolific factory for these particles. Theorists suggest that streams of solar actions are constantly streaming out from the sun, passing through Earth completely unnoticed. To catch one, scientists have devised a clever trick based on a phenomenon predicted by quantum theory. In the presence of a tremendously powerful magnetic field, an action could potentially convert into a photon of light, a particle we can actually see. This is the core principle behind ambitious experiments like the Action Dark Matter experiment, or ADMX. Imagine a high-tech listening device, a resonant cavity cooled to temperatures colder than deep space, placed inside the world's most powerful magnets. Researchers slowly tune this cavity, like turning the dial on a cosmic radio, listening for the specific frequency at which the dark matter action field might ring and convert into a faint microwave photon. They are essentially listening for the universe's quietest whisper, a signal so weak that it would be drowned out by the thermal vibration of a single cell in your body. The detection of an action would be a monumental achievement, a two-for-one discovery that simultaneously solves a fundamental problem in particle physics and reveals the identity of the universe's dominant matter. It would show us that the dark cosmos is not a collection of heavy phantoms, but an ocean of ultra-light waves, a concept that challenges our very imagination and opens up a new frontier in our quest to understand the hidden architecture of reality. Now, let's turn our attention to a particle that is already known to be a cosmic ghost and consider what would happen if it had an even more elusive, shadowy twin. We are familiar with neutrinos, those near massless particles produced in the hearts of stars and in violent cosmic events, famous for their ability to pass through light years of lead without a single interaction. But what if our current understanding of these phantoms is incomplete? This brings us to our third theory, which proposes the existence of a new type of neutrino, one so detached from our reality that it's called the sterile neutrino. Think of the standard neutrinos we know as ghosts that can, on extremely rare occasions, still make their presence felt by bumping into other particles via the weak nuclear force. A sterile neutrino, by contrast, would be a ghost of a ghost. It would be completely immune to both the weak force and the strong nuclear force. It would not feel electromagnetism, so it would be utterly dark and invisible. Its only connection to the rest of the universe would be through the fabric of gravity itself. This profound isolation is what makes it such a compelling dark matter candidate. A universe filled with sterile neutrinos would be exactly what we observe, a cosmos with a massive, invisible gravitational pull that guides the formation of galaxies, yet leaves no other trace. The theoretical framework for these particles is deeply elegant. It suggests that the three known types of neutrinos, electron, muon, and tau neutrinos, could periodically oscillate or transform into their sterile counterparts as they travel through space. This would explain certain quirks in data from neutrino experiments that have long puzzled physicists, but the most tantalizing clue for sterile neutrinos doesn't come from Earth-bound labs, but from the depths of intergalactic space. Several years ago, astronomers studying the combined X-ray light from distant galaxy clusters and the Andromeda galaxy detected a faint, mysterious signal, an emission line at a very specific energy that didn't correspond to any known atomic transition. This was an X-ray whisper with no obvious source. The most exciting explanation proposed was that this signal was the death rattle of a sterile neutrino. The theory goes that these particles, while stable over cosmic timescales, are not entirely immortal. A very small fraction of them could spontaneously decay into an ordinary, active neutrino and a photon of X-ray light. The collective decay of countless sterile neutrinos drifting through the vast clouds of dark matter in these galaxy clusters could produce exactly the kind of faint, uniform X-ray glow that was observed. It was a potential smoking gun, a direct, observable signature of dark matter decaying right before our eyes. However, the path to a discovery is never straightforward in frontier science. This result remains one of the most hotly debated anomalies in modern physics. Subsequent observations with newer X-ray telescopes have failed to conclusively confirm the signal in other celestial objects, casting doubt on its interpretation. The scientific community is divided, with some researchers convinced they are seeing the first glimpse of a hidden particle, and others attributing the line to more mundane, though still poorly understood, plasma physics processes or instrumental effects. The pursuit is far from over. New, more sensitive X-ray observatories are being planned, designed specifically to scan the sky for this enigmatic signal with unprecedented precision. The story of the sterile neutrino is a perfect example of how science operates at its cutting edge. It's a dance between bold theoretical prediction and elusive, controversial data. It demonstrates how a single, unexplained flicker of light from the cosmos can ignite a decades-long quest, driving us to refine our instruments and sharpen our theories in the hope of catching a shadow. Shifting our focus from the constituents of dark matter to the very fabric of force itself, we arrive at a particle that is arguably the most fundamental of them all, even though it has never been seen. This is the graviton, the hypothetical messenger of gravity. You are familiar with the other fundamental forces. Electromagnetism has the photon, the strong nuclear force has gluons, and the weak force has the W and Z bosons. Each of these forces is transmitted by its own special type of particle, operating within the quantum realm. For gravity to take its rightful place in this quantum family, it too needs a carrier particle. The graviton is that missing piece, the quantum of gravity. Its existence is the key to the holy grail of theoretical physics, a single, unified theory that seamlessly merges the rulebook of the very small quantum mechanics with the rulebook of the very large Einstein's general relativity. For a century, these two pillars of modern physics have been famously at odds. General relativity describes gravity as the elegant warping of spacetime, a smooth, continuous landscape. Quantum mechanics, on the other hand, describes a world of frenetic, discrete packets of energy and probability. Unifying them is essential to understanding the most extreme environments in the cosmos, like the singularities at the hearts of black holes or the very first moments of the Big Bang, where both immense gravity and quantum effects must have ruled supreme. The graviton is the proposed bridge between these two worlds. Theorists predict that just as a charged particle interacting with another emits a photon, any object with mass, like a planet or a person, would be constantly emitting and absorbing gravitons, creating the gravitational pull we experience. This is an elegant idea, but it leads to an almost insurmountable challenge: detection. The reason finding a graviton is considered the most difficult experiment conceivable is due to the astonishing weakness of gravity as a force. To put it in perspective, the gravitational attraction between two protons is about 10 to the power of 36 times weaker than the electromagnetic repulsion between them. This means that the probability of a single graviton interacting with a particle in a detector is so infinitesimally small that it borders on the impossible. You could build a detector made of pure lead with the mass of Jupiter and place it in orbit around a neutron star, and you might still only expect to see a handful of graviton interactions over the entire age of the universe. This profound weakness is why we don't see gravity in the quantum world. It is completely drowned out by the other forces. Yet, a monumental breakthrough in 2015 provided what many consider the first indirect but powerful evidence that gravitons must exist. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first direct detection of gravitational waves, ripples in the fabric of spacetime itself, caused by the collision of two black holes over 1 billion light-years away. If we think of gravity as a field, then these ripples are vibrations within that field. And in the quantum picture, where fields are composed of particles, a vibration in the gravitational field is by definition a wave made of gravitons. The detection of gravitational waves was like hearing the collective hum of a vast choir of gravitons. While we haven't isolated a single singer, we have heard the choir's music, confirming that the gravitational field can be excited and can carry energy in waves, just as the electromagnetic field carries light. This discovery doesn't prove the existence of individual gravitons beyond all doubt, but it strengthens the case immensely. It tells us that we are on the right track, that the quantum description of gravity is likely valid, and that the universe in its deepest workings speaks a quantum language. The hunt for the graviton therefore moves from trying to catch one in a detector to a more nuanced pursuit, studying the properties of gravitational waves with ever greater precision, looking for tiny quantum imprints in the ripples from the most cataclysmic events in the cosmos, hoping to find the subtle signature of the particle that literally holds the universe together. Now we venture into one of the most beautiful and ambitious ideas in all of theoretical physics, a framework so compelling that it promised to solve multiple cosmic puzzles at once. This is supersymmetry, or SUSY for short, At its heart, supersymmetry is a proposal of profound cosmic balance. It suggests that for every known particle in the universe, every electron, every quark, every photon, there exists a hidden super-partner particle. These are often whimsically called sparticles. The electron would have a partner called the selectron. The quark would be matched with the squark. Even the force-carrying particles like the photon would have a shadowy counterpart, the photino. This isn't just about doubling the particle zoo for fun. It's a fundamental symmetry of nature that would elegantly unite the two great families of particles, the fermions, which are the building blocks of matter, and the bosons, which are the messengers of force. In a supersymmetric universe, the distinction between matter and force begins to blur, revealing a deeper, more harmonious reality. The implications of this are staggering. For one, it provides a perfect and natural candidate for dark matter. In most supersymmetric models, these sparticles are created in the fiery first moments of the Big Bang. As the universe expanded and cooled, all the heavier, unstable sparticles would have decayed away, cascading down into lighter and lighter states. But this decay chain would have a natural endpoint, a stable particle that has no lighter state to decay into. This particle, the lightest supersymmetric particle, or LSP, would be absolutely stable, electrically neutral, and interact only very weakly with ordinary matter. It would be a relic frozen out from the hot early universe, and its gravitational influence would be exactly what we observe as dark matter. The neutralino, a specific mixture of the partners of the photon, the Z boson and the Higgs boson, became the golden candidate, a WIMP-like particle that emerged not from ad hoc guesswork, but from a beautiful theoretical structure. For decades, supersymmetry was the frontrunner, the theory that felt so right. It didn't just explain dark matter, it also solved a major headache in the standard model concerning the mass of the Higgs boson. Without supersymmetry, quantum corrections should have driven the Higgs mass to an astronomically high value, a problem known as the hierarchy problem. Sussy partner particles would naturally cancel out these corrections, making the relatively light mass of the Higgs we eventually found seem natural and inevitable. The stage was set for a triumphant discovery. With the restart of the Large Hadron Collider, the most powerful particle accelerator ever built, physicists were confident they would soon see the first sparticles. The energy scales were right, the theoretical arguments were persuasive, the excitement was palpable, but then the data started coming in. The LHC performed magnificently, colliding protons at unprecedented energies and collecting mountains of data. Researchers sifted through the debris of countless collisions, searching for the telltale missing energy that would signal a sparticle zipping away undetected. Yet, one by one, the potential hiding places for these particles have come up empty. The simplest and most elegant versions of supersymmetry, which predicted sparticles light enough to be found at the LHC's current energy, have been largely ruled out. This has been a profound disappointment for the physics community. The dream of a complete and elegant solution hasn't vanished, but it has been forced to evolve. Supersymmetry is a flexible theory, and proponents have adjusted the models, pushing the expected masses of these sparticles to higher, less accessible energy scales. The search continues, and the hope is that the next generation of colliders or more sensitive indirect searches might yet reveal this hidden symmetry of nature. The story of Sussy is a powerful lesson in how science progresses. It shows us that even the most beautiful and compelling ideas must ultimately bow to experimental evidence. The universe is under no obligation to conform to our aesthetic preferences, no matter how elegant they may seem. The quest for supersymmetry has pushed our experimental capabilities to their limits and deepened our understanding of what is possible, reminding us that the greatest discoveries often lie just beyond our current reach, waiting for the next leap in our imagination and our technology. Leaving behind the symmetrical world of supersymmetry, we encounter a concept so fundamental it challenges a principle you've likely known since your first childhood magnet: that every magnet, no matter how small, always has both a north and a south pole. Break a bar magnet in half and you don't get isolated poles. You simply create two new magnets, each with its own north and south. This duality seems like an unbreakable law of nature. But what if it isn't? This brings us to the magnetic monopole, a hypothetical particle that would carry only one magnetic charge, a pure north or a pure south. The idea of such a particle is not new. The foundational equations of electromagnetism, formulated by James Clerk Maxwell in the 1860s, would become even more beautiful and symmetric if monopoles existed. You see, we have isolated electric charges. We call them electrons and protons, but we have never found an isolated magnetic charge. This asymmetry has bothered physicists for over a century. The true modern impetus for monopoles, however, came from the grand unified theories of the 1970s. These are some of the most ambitious frameworks in physics, attempting to describe how the three fundamental non-gravitational forces, the electromagnetic, the weak, and the strong nuclear forces, were once a single, unified force in the extreme energy and temperature of the universe's first moments. As the cosmos expanded and cooled, this perfect symmetry was broken, much like water freezing into ice crystals. The forces we see today are the frozen fragments of that primordial unity. And here's the stunning prediction. When this phase transition happened, when the unified force splintered, the fabric of spacetime would have developed defects, topological knots in the fields that could not smooth themselves out. These defects would manifest as particles, and not just any particles, but magnetic monopoles. They would be incredibly heavy, perhaps as massive as a bacterium, which is colossal for a fundamental particle, and they would possess a monstrously powerful magnetic charge. Finding a single monopole would be a direct validation of grand unification. It would provide concrete evidence that the forces we see as separate and distinct were indeed one in the early universe. It would fundamentally rewrite our textbooks on electromagnetism, completing a symmetry that has been staring back at us for 150 years. The hunt for these legendary particles has been one of the most creative and persistent endeavors in modern science. Given their predicted immense mass, you couldn't create one in any particle accelerator we could possibly build. The energies required are trillions of times beyond the reach of the Large Hadron Collider. So, if they exist, they must be relics left over from the Big Bang, drifting through the cosmos as cosmic fossils. The challenge is to find one. Early searchers were ingenious. Physicists realized that if a monopole passed through a loop of wire, it would induce a detectable electric current, a clear, unambiguous signal. They used superconducting loops which can carry current indefinitely without resistance, and placed them in deep mines or under the Antarctic ice, waiting for the sudden, persistent jump in current that would signal a monopole's passage. The most famous of these experiments, led by physicist Blas Cabrera in 1982, recorded an event that was a perfect signature for a monopole. It caused immense excitement, but the signal never repeated. To this day, no one knows for certain if it was a fleeting glimpse of a cosmic ghost or an obscure instrumental glitch. Other methods have involved examining ancient rocks and minerals. The idea is that a heavy, charged monopole would leave a trail of damage as it plowed through solid matter, a track that could be etched out and seen under a microscope. Scientists have even searched for monopoles in samples of moon rock, free from Earth's atmospheric interference. More recently, some of the most sensitive searches have been conducted using large particle detectors, not unlike those used for the hunt for dark matter. Experiments like the macro detector in Italy and the Ice Cube Observatory at the South Pole have analyzed vast amounts of data, looking for the unique and energetic signature a monopole would leave as it moved through the detector medium. So far, all these searches have come up empty. The monopole remains elusive, yet the search continues because the prize is so profound. Discovering a magnetic monopole would be like finding a Rosetta Stone for the fundamental forces. It would provide a direct window into the universe when it was a fraction of a second old, confirming our most ambitious theories about cosmic unity and revealing that the deepest symmetries of nature are written not just in the laws of physics, but in the very particles that were forged in the first instant of time. As we've explored the hidden particles that could make up the dark universe, we've largely focused on the matter part of dark matter. But what about the forces that might govern this shadow realm? Just as our visible universe is held together by forces carried by particles like the photon and the gluon, could there be a whole set of hidden forces acting on dark matter? This leads us to a fascinating and elegant possibility, the dark photon. Imagine our familiar photon, the particle of light and the carrier of the electromagnetic force. Now envision a shadowy counterpart, a particle that acts as the force carrier for a hypothetical dark sector. A whole universe of particles and interactions that is completely invisible to us, operating in parallel to our own. This is the dark photon. It wouldn't carry our kind of light, but it could mediate a dark electromagnetism that allows dark matter particles to interact with each other, potentially forming dark atoms, dark molecules, or even complex dark structures we can scarcely imagine. The most compelling aspect of this theory is that this dark sector might not be entirely isolated. There could be a tiny, fragile bridge between our world and the dark one. The dark photon, in some models, is theorized to have a minuscule coupling to our ordinary electromagnetic force. It's as if the photon and the dark photon are distant cousins who share a faint, almost imperceptible family resemblance. This tiny connection opens up a revolutionary possibility for detection. We might not need to catch a dark matter particle itself. We could instead detect the subtle influence of its hidden force carrier. The way physicists search for this phantom particle is incredibly clever. They are essentially looking for missing energy and momentum in incredibly precise experiments. One prominent method involves using particle accelerators. When electrons and their antimatter partners, positrons, are made to collide at high speeds, they annihilate and produce a burst of pure energy, which typically transforms into a spray of known particles. But if dark photons exist, occasionally this energy could instead create one of them. This dark photon would then be invisible to the detector. It would simply fly away, carrying its energy with it. The only sign it ever existed would be a precise amount of energy and momentum that seems to vanish into thin air. This isn't a flaw in the experiment, it's a potential signal, a ghostly footprint left by a particle from the dark sector. Another ingenious approach looks for the dark photon's influence not in high-energy collisions, but in the quiet world of atomic physics. The theory suggests that this faint mixing between the ordinary photon and the dark photon could cause a slight shift in the energy levels of atoms. It would be an almost immeasurably small effect, like a whispered secret altering the precise ticking of an atomic clock. Experiments are now so sensitive that they can probe these energy levels with astounding accuracy, looking for any tiny deviation from what the standard model predicts. Finding such an anomaly would be a monumental clue, pointing directly to the presence of a hidden force subtly tugging at the fabric of our reality. Perhaps the most dramatic possibility is that dark photons could be the key to finally making dark matter interact with our detectors. If dark matter particles are held together by a dark electromagnetic force, then occasionally, a dark photon might oscillate into an ordinary photon, producing a faint, unexpected burst of light in a detector. Or a dark matter particle could interact with an ordinary particle by exchanging a virtual dark photon, a process that would deposit a tiny amount of energy that we could potentially measure. This transforms the search for dark matter from a direct hunt for a single, elusive particle into a broader quest to map the entire hidden ecosystem it might inhabit. The pursuit of the dark photon represents a fundamental shift in strategy. It acknowledges that dark matter might not be a single, simple particle waiting to be found, but part of a rich and complex hidden world with its own laws and interactions. Discovering a dark photon would be like finding a secret passageway in a vast dark castle. We wouldn't be inside the castle yet, but we'd have found the door, and we'd finally have a way to peer through the keyhole and begin to understand the mysterious architecture of the cosmos that has been hidden from our view since the dawn of time. What if we have been searching in the wrong place entirely, looking for exotic new particles when the answer has been lurking in the most extreme objects gravity can create? This brings us to one of the most provocative ideas in modern cosmology, the possibility that dark matter is not made of particles at all, but is instead composed of black holes. Not the stellar mass black holes formed from collapsing giant stars, or the supermassive behemoths at the centers of galaxies, but a vast population of primordial black holes that could have formed in the universe's first chaotic second. The concept is as elegant as it is startling. In the incredibly dense and hot environment just after the Big Bang, random fluctuations in density could have been so extreme that pockets of space spontaneously collapsed under their own gravity, pinching off into tiny black holes. These wouldn't require the death of a star, they would be birthmarks on the fabric of the newborn cosmos itself. For this idea to work as a dark matter candidate, these primordial black holes would need to be abundant and fall within a specific mass range. A leading contender suggests they could have masses comparable to a large asteroid, perhaps around the mass of the dwarf planet Ceres. Envision a black hole no larger than a baseball, yet containing the mass of a mountain, and then picture trillions upon trillions of these objects swarming through every galaxy, their collective gravity dictating the rotation of stars and the bending of light. They would be the perfect dark matter, massive, invisible, and interacting only through the force of gravity. The appeal of this theory is its stark simplicity. It requires no new physics beyond general relativity and our standard model of cosmology. It just repurposes one of gravity's most dramatic phenomena to solve its greatest mystery. For decades, this idea was largely sidelined. The original models from the 1970s that considered planet-sized or larger primordial black holes ran into major problems. Such large, numerous black holes would have left observable imprints on the cosmic microwave background, the leftover radiation from the Big Bang, and would have disrupted the delicate process of forming the first light elements. These observations effectively ruled out a universe where dark matter is primarily made of black holes heavier than a certain threshold. But science evolves, and as our understanding of the early universe deepened, theorists realized that a specific, narrow window of smaller masses remained wide open. An asteroid mass population of primordial black holes could have evaded all these constraints, floating through the cosmos as a ghostly, undetected mass. The hunt for these objects then turned to a phenomenon known as gravitational microlensing. The principle is brilliant in its application. If a primordial black hole were to pass directly between Earth and a distant star, its gravity would act as a lens, bending the starlight and causing the star to temporarily brighten. The duration of this brightening is directly related to the mass of the foreground object. For an asteroid mass black hole, this flash would be incredibly brief, lasting only a fraction of a second. To catch these fleeting events, astronomers have employed powerful, wide-field telescopes that monitor hundreds of millions of stars in nearby galaxies, such as the Magellanic Clouds, for years on end. Projects like the Optical Gravitational Lensing Experiment, or OGLE, and the Subaru Telescope's monitoring program have collected immense datasets. The results have been intriguing but ultimately limiting. While a handful of candidate events have been spotted that are consistent with such small black holes, there simply aren't enough of them to account for all the dark matter. The microlensing surveys have placed stringent upper limits, suggesting that primordial black holes in this mass range could make up no more than a small percentage of the dark matter budget. It seems the galaxy is not teeming with enough of these tiny dark lenses to solve the mystery alone. Just as this line of evidence was casting doubt on the theory, a spectacular discovery from an entirely different field breathed new life into it. When the LIGO Observatory made its first historic detection of gravitational waves in 2015, the signal came from the merger of two black holes, each about 30 times the mass of our Sun. This was a surprise. Astronomers had not expected to find so many black holes of that size. Where did they come from? One compelling explanation is that they were themselves primordial black holes formed in the early universe. If true, it would mean that at least a fraction of the dark matter could indeed be in the form of these ancient gravitational fossils. The debate is now more nuanced than ever. Perhaps dark matter is not a single thing. Maybe it's a composite, with a portion being some kind of undiscovered particle like an axion or a WIMP, and another portion consisting of a spectrum of primordial black holes, from asteroid-sized ones to the stellar mass ones seen by LIGO. This hybrid approach acknowledges that the cosmos is rarely simple, and that its greatest secrets may be held by more than one keeper. The search continues, with new proposals to use the entire solar system as a detector. The idea is that if an asteroid-mass primordial black hole were to pass through our neighborhood, its gravitational tug would minutely perturb the orbits of the planets. By tracking the positions of planets and spacecraft with exquisitely precise radio telescopes over decades, we might one day detect the subtle wake left by one of these cosmic ghosts as it silently drifts through our celestial backyard. Now, let's stretch our imaginations beyond the 3 dimensions of space we experience every day and venture into a realm where the universe has more hidden directions than we can see. This brings us to a concept that sounds like science fiction but is taken with the utmost seriousness in theoretical physics: Kaluza-Klein particles. The story begins nearly a century ago with a brilliant insight from mathematician Theodore Kaluza. He demonstrated that if you wrote Einstein's equations of general relativity in a universe with not 3, but 4 spatial dimensions, and then carefully compactified or curled up that extra dimension into a circle so tiny it was undetectable, a remarkable thing happened. From the perspective of a 3-dimensional observer, the equations of gravity naturally gave rise to a second set of equations, those of James Clerk Maxwell's electromagnetism. In one elegant stroke, gravity and light were unified not by force but by geometry. The idea was revolutionary, suggesting that the forces of nature could be the geometric shadows of hidden dimensions. This concept was refined by Oscar Klein, who proposed that the reason we don't see this extra dimension is that it is curled up on a scale far smaller than an atom, a scale known as the Planck length. Now, let's bring this profound idea into the modern quest for dark matter. In contemporary versions of this framework, particularly in theories with more than one extra dimension, every known particle has a unique way of moving through these compactified dimensions. Think of it like this: imagine a guitar string. It can vibrate in a fundamental mode, producing the lowest note, but it can also vibrate in higher harmonics, producing a series of overtones. In a similar way, a particle like an electron moving through a tiny, curled-up dimension doesn't just have one state. It has a whole tower of possible vibrational states, each corresponding to a heavier version of itself. These are the Kaluza-Klein particles. From our 3-dimensional viewpoint, we would see not just one electron, but an entire family of partner electrons, each with a progressively larger mass. The lightest one would be the electron we know and love. The next one up the tower might be thousands of times heavier, a massive shadow electron. This replication applies to every particle in the Standard Model, creating a vast hidden zoo of heavy partners. So, how does this connect to the dark matter mystery? In many of these models, a symmetry exists that makes the lightest particle in this entire Kaluza-Klein tower absolutely stable. It has no lighter state to decay into, and it is often electrically neutral and weakly interacting. This particle becomes a perfect dark matter candidate. Imagine, for instance, that the photon has a Kaluza-Klein partner. The first heavy vibration in the photon's tower would be a massive, stable particle that doesn't interact with light but does feel gravity. Vast numbers of these particles would have been produced in the hot, early universe when energies were high enough to excite these vibrational states. As the cosmos cooled, all the heavier, unstable Kaluza-Klein particles would have decayed away, eventually transforming into the lightest, stable one. The universe would now be filled with this relic, a cosmic fossil from the era of higher dimensional physics, and its gravitational influence would be exactly what we attribute to dark matter. The beauty of this theory is its deep connection between two of physics' greatest puzzles. It suggests that the missing mass in the universe is not just some random particle, but a direct signature of the hidden geometry of space itself. The reason galaxies hold together is because of the gravity of particles that are, in essence, vibrations in the compactified fabric of higher dimensions. Detecting such a particle would be a twofold revelation, confirming the existence of dark matter and providing the first experimental evidence that our universe has more dimensions than we can see. The hunt for these particles is incredibly challenging. Their immense mass means they are far beyond the direct reach of current particle colliders. However, just as with WIMP, physicists search for them indirectly, looking for their annihilations in space or for the rare occasions when they might bump into a nucleus in a deep underground detector. A confirmed signal would be a whisper from the higher dimensional architecture of reality, telling us that the true nature of the cosmos is woven into dimensions folded away into a size so infinitesimally small, yet whose influence on the universe is literally cosmic. But what if the solution to the dark matter puzzle isn't just a single particle, but an entire parallel cosmos existing right alongside our own? This is the breathtaking premise of our 10th theory, which posits the existence of a complete mirror universe. The idea stems from a deep observation about the laws of physics themselves. When we look at the equations governing particles and forces, we notice a profound symmetry. For every fundamental particle, there seems to be a potential for a perfect mirror image counterpart, a doppelganger with identical properties. This mirror symmetry isn't just a mathematical curiosity, it could be a fundamental feature of reality. In this scenario, the mirror universe would be a perfect replica of our own in terms of its laws, containing mirror protons, mirror electrons, and even mirror light. However, these mirror particles would be completely invisible to us because they do not interact with any of our fundamental forces, not electromagnetism, not the strong nuclear force, and not even the weak nuclear force. The only bridge between our world and the mirror world would be the universal glue of gravity. Mirror matter would feel the gravitational pull of our matter, and our matter would feel its pull in return. This means that for every star and galaxy we see, there could be a mirror star and a mirror galaxy occupying the exact same region of space, yet forever unaware of each other's presence, bound only by their mutual gravity. The collective gravitational influence of all this mirror material would perfectly explain the dark matter that holds galaxies together and shapes the cosmos on the largest scales. One of the most compelling aspects of this theory is how it could resolve a long-standing mystery in the field of astronomy involving white dwarf stars. These are the dense, Earth-sized embers left behind when stars like our Sun exhaust their nuclear fuel. Astronomers can measure the temperature and brightness of these stellar corpses, and by understanding their composition and age, predict how quickly they should be cooling down. However, observations have revealed that some white dwarfs are cooling at an anomalously fast rate. They are dimming faster than our models can account for. The mirror matter theory offers an elegant explanation. If a white dwarf star has accumulated even a tiny amount of mirror matter in its core over its lifetime, at perhaps just 1% of its total mass, this invisible component could dramatically alter its thermal properties. Normal matter and mirror matter would be transparent to each other. The mirror nuclei wouldn't block the flow of photons from the normal matter, but they would provide a new, highly efficient channel for cooling. The heat from the normal matter could be transferred to the mirror matter, which would then radiate that energy away as mirror photons. Invisible light that carries the heat out of the star and into the hidden cosmos, causing the white dwarf to fade much more rapidly than expected. This would be a subtle but measurable signature of the mirror world's existence, a cosmic chill whispering of a parallel reality. Other potential signatures are even more dramatic. If mirror matter can form mirror atoms and mirror molecules, it might be able to coalesce into mirror planets or even entire mirror stars. These objects would be completely dark to our telescopes, yet their immense gravity would be detectable. A mirror star orbiting a normal star would cause the visible star to wobble in a way that suggests an unseen companion, but one that emits no light whatsoever. There's even the speculative possibility of mirror life, complex structures built from mirror chemistry, evolving entirely in the dark, forever separated from our world by the fundamental barrier of force. The search for this mirror reality is pushing experimental physics to its limits. Scientists are looking for tiny deviations in the behavior of neutrons, which might occasionally oscillate into their mirror counterparts and disappear from our view. Others are designing ultra-sensitive force experiments to see if gravity behaves slightly differently at microscopic distances, which could be a sign of extra dimensions or the subtle influence of mirror forces. The mirror matter theory transforms the dark matter problem from a hunt for a single ghostly particle into a profound cosmological question. It suggests we are not alone in the universe in the most fundamental sense possible. We share our space with an entire shadow cosmos, a silent partner in the cosmic dance, whose presence we can only infer through the gentle, persistent tug of gravity. Now, let's explore an object so strange it blurs the line between a fundamental particle and a cosmic lump of field energy. This is the cue ball, a hypothetical and exotic entity predicted by some versions of supersymmetry. To understand a cue ball, you first have to let go of the idea that all matter is made of point-like particles. Instead, picture a stable, organized clump of field, a sort of bubble or droplet in the fabric of space itself. This isn't a random fluctuation. It's a coherent, spherical lump of squarks, leptons, and Higgs fields, the supersymmetric partners of our familiar quarks, electrons, and the Higgs boson, all holding themselves together in a perfect, self-sustaining quantum state. The Q in its name stands for a conserved quantum charge, and the ball describes its shape. What makes a Q ball so fascinating as a dark matter candidate is its potential for incredible stability and immense mass. Unlike a single WIMP or action, a single Q ball could be astronomically heavy, potentially ranging from the mass of a proton all the way up to the mass of an asteroid, all contained within a single macroscopic object. Because its stability comes from its overall quantum configuration rather than from being the lightest particle, a Q ball could be absolutely indestructible, a permanent fossil from the early universe. Its interaction with ordinary matter would be extraordinarily weak. It would essentially be a transparent, massive globe drifting silently through space, its only significant influence being its gravitational pull. This means a population of these objects scattered throughout galaxies could easily account for the missing mass we call dark matter. The methods required to detect such an entity are as bizarre as the object itself. Traditional particle detectors, which look for tiny nuclear recoils from a WIMP collision, would be completely useless. A Q ball is not a bullet, it's more like a ghostly, super-dense weather balloon. If one were to pass through a planet like Earth, it wouldn't leave a trail of ionized atoms like a normal particle. Instead, its passage would be so smooth and coherent that it might only be detectable through incredibly subtle effects. One proposed method involves monitoring large volumes of material for a specific type of signature. As a Q ball moves through ordinary matter, its constituent supersymmetric fields could catalyze the decay of protons, a process that is otherwise exceptionally rare. This would cause a burst of radiation along its path. Another idea is that a cue ball could interact with the magnetic fields within a planet or star, generating a unique, low-frequency electromagnetic pulse. The most dramatic possibility, however, involves the sheer mass of these objects. An asteroid mass cue ball passing through the solar system would exert a tiny but measurable gravitational tug on the planets and our interplanetary spacecraft. By tracking the trajectories of probes like Voyager or Cassini with extreme precision, astronomers could, in theory, detect the minute wobble induced by one of these cosmic ghosts as it drifts through our celestial neighborhood. The hunt for cue balls, therefore, represents a radical departure from conventional particle physics. It's a search not for a speck, but for an invisible, intangible, and potentially mountain-sized object that could be floating right past us. Finding one would not only solve the dark matter puzzle, but would also provide direct, spectacular proof that the supersymmetric fields we theorize about are real and can condense into stable, macroscopic structures, revealing a layer of material reality far more complex and wondrous than we ever anticipated. Just when you thought dark matter candidates couldn't get any more extreme, we encounter a true behemoth, a particle so colossal it makes even the heaviest WIMP seem feather-light. Welcome to the realm of WIMPs. The name itself, a playful nod to the classic movie monster, is perfectly fitting. These are hypothetical dark matter particles with masses that are almost incomprehensible, potentially 1 trillion times heavier than a proton or even more. To put that into perspective, a single WIMP could have a mass comparable to a living bacterium, an entire microbe's worth of mass packed into a single, fundamental point. This isn't just a minor adjustment to the dark matter search, it's a leap into an entirely different regime of physics. The existence of such particles forces us to confront a profound question: how could anything so heavy and dense possibly be created? The answer lies in the very first moments of the universe, during a period of exponential expansion known as cosmic inflation. In the chaotic aftermath of inflation, as the fabric of space-time was settling down, it wouldn't have been perfectly smooth. Theorists propose that violent, random fluctuations in gravitational and other fields could have directly crystallized into particles. This mechanism, known as gravitational production, doesn't rely on the high-temperature particle collisions of the later Big Bang. Instead, it's as if the ringing of spacetime itself, like a struck gong, froze into permanent, massive vibrations. These vibrations became the WIMPs, born not from fire, but from the raw geometry of the newborn cosmos. Their incredible mass is both their defining feature and the reason they are so elusive. You simply cannot create a WIMPs in any particle accelerator, not even the Large Hadron Collider. The energies required are far beyond our technological reach, residing at a scale that likely only existed at the very birth of the universe. Furthermore, their immense weight makes them incredibly sluggish. Unlike lighter dark matter particles that might zip around at significant fractions of the speed of light, WIMPs would be moving at a relative crawl, a sea of ultra-heavy, slow-moving ghosts permeating every galaxy. This has a direct consequence for how we might search for them. Because they are so heavy and stable, they wouldn't annihilate with each other in large numbers to produce detectable radiation, a common search strategy for lighter WIMP. Instead, the hunt for WIMPs relies on more subtle, indirect astrophysical signatures that test the very limits of our observational capabilities. One of the most promising methods involves looking for the fingerprints of these super-heavy particles on the smallest structures in the universe. Dark matter isn't just a smooth, featureless cloud. It clumps together under its own gravity, forming a cosmic scaffolding upon which galaxies are built. The properties of the dark matter particle itself determine how efficiently it can form these clumps, especially on small scales. Cold, slow-moving dark matter, like WIMP or Axions, is very good at clumping, leading to a universe filled with countless small satellite dwarf galaxies. WIMPs, however, are so massive and slow that they exhibit a unique property. Their quantum mechanical wavelengths are incredibly small, meaning they behave more like classical particles and less like spread-out quantum waves. This allows them to form clumps on even tinier scales than other candidates. Astronomers are now using powerful telescopes to census the population of the very smallest and faintest dwarf galaxies orbiting our Milky Way. Finding an overabundance of these tiny, dark matter-dominated galaxies could be a hint that the dark matter is made of something super heavy like WIMPs, as their unique physics would have seeded a richer harvest of microgalaxies in the early universe. Another, even more exotic signature involves the potential for WIMPs to decay. While they are theorized to be stable over the current age of the cosmos, some models allow for a tiny, slow decay process. If a WIMP with a mass of 1 trillion protons were to decay, it would release an astonishing amount of energy, transforming into a burst of ultra-high-energy cosmic rays or gamma rays. These would be among the most energetic particles ever observed in the universe. Observatories like the Pierre Auger Observatory, which watches for rare, high-energy particles striking Earth's atmosphere, are constantly scanning the skies. If a consistent, diffuse background of these ultra-high-energy events were found, coming from all directions, it could be the collective death rattle of the WIMPs population, the final whisper of a particle born in the first instant of time. The search for WIMPs pushes cosmology to its frontier, asking us to use the entire universe as a laboratory to probe physics at energy scales we can never hope to recreate. It is a testament to the creativity of physicists that they can devise ways to hunt for an object that is both smaller than an atom and heavier than a bacterium, a true cosmic paradox that may hold the key to the dark universe. For decades, the prevailing image of dark matter has been that of a perfect ghost, not only invisible to us, but utterly indifferent to its own kind. This cold and collisionless model is incredibly successful at explaining the universe on the largest scales, the grand tapestry of galaxy clusters and the cosmic web. But when we zoom in to look at individual galaxies, this simple picture begins to fray at the edges, revealing small-scale puzzles that have nagged at astronomers for years. One of the most persistent is known as the cusp core problem. According to supercomputer simulations of the cold, collisionless model, dark matter should pile up in a very specific way at the centers of galaxies. The density should rise steeply, creating a sharp peak or a cusp at the very heart of every galaxy, including our own Milky Way. Yet, when astronomers measure the rotation speeds of stars and gas in the inner regions of small, faint dwarf galaxies, they find something quite different. Instead of a steep cusp, the dark matter seems to be distributed in a much flatter, gentler core. It's as if someone took a knife and carefully smoothed out the very center of the dark matter halo. This is a major discrepancy between theory and observation, a clear sign that our understanding of dark matter's fundamental nature might be incomplete. How could this happen if dark matter particles are truly collisionless, passing through each other like spirits in the night? What physical process could have redistributed them to create these flat cores? This is where our 13th theory offers a radical and compelling solution. What if dark matter isn't entirely antisocial? What if it possesses its own hidden force, allowing it to interact with itself? This is the world of self-interacting dark matter. In this scenario, dark matter particles wouldn't just feel gravity, they would also feel a new fifth force that acts only within the dark sector. Think of it as a private conversation happening in a language only they understand. These particles could bump off each other, scatter, and exchange momentum, creating a form of dark matter pressure. Now imagine a young galaxy forming. In the standard model, dark matter particles swing through the dense center on very elongated orbits, piling up to create that sharp cusp. But in a self-interacting dark matter universe, every time two particles come close in that dense central region, they collide and scatter. This constant billiard ball-like interaction transfers energy from the fastest-moving particles on the outskirts to the slowest ones in the core. This process effectively heats up the central core, causing it to expand and puff up, transforming what would have been a sharp density peak into a soft, flat core, beautifully matching the observations in dwarf galaxies. The evidence for this social dark matter isn't limited to the structure of small galaxies. Some of the most dramatic support comes from colossal cosmic crashes, the collisions of entire galaxy clusters. The most famous of these is the Bullet Cluster, a system where two galaxy clusters have slammed into each other at millions of miles per hour. In such a collision, the different components of the clusters behave in telling ways. The hot gas, which makes up most of the ordinary matter, is like a fluid. It smashes into the gas from the other cluster, slows down dramatically due to friction, and gets stuck in the middle. The stars, because they are so spread out, mostly pass right through each other without colliding, and the dark matter, as traced by its gravitational lensing effect, also appears to sail right through the collision. In the Bullet Cluster, the dark matter clumps are found far ahead of the stalled gas, which was a landmark proof that dark matter exists and is largely collisionless with respect to ordinary matter. However, more recent studies of other cluster collisions have added a fascinating twist. In a system known as the Abell 5208 cluster, astronomers observed something that made headlines. The dark matter appeared to be lagging behind the galaxies. It was as if, during the collision, the dark matter had experienced some kind of drag, not from the ordinary gas, but from itself. This is exactly the kind of signature self-interacting dark matter would produce. When two dark matter halos collide, the particles within them could be scattering off each other, slowing down their overall motion and creating a slight separation from the stars that simply passed through unimpeded. This single observation isn't conclusive proof, but it is a tantalizing hint that dark matter might have a rich and complex social life after all. The implications of this are profound. If dark matter can interact, it opens the door to a whole new dark sector physics. Could dark matter form bound states or even dark atoms? Could it have a form of dark radiation that carries away energy? The possibility of self-interactions forces us to consider that the dark universe might be as dynamic and structured as the visible one, a shadow world with its own intricate rules and relationships, forever hidden from our view, but whose subtle gravitational effects are slowly revealing its true, complex nature. Now, we journey from the realm of colossal WIMP-zillas to the opposite end of the spectrum, to a candidate so lightweight it challenges our very notion of what a particle can be. This is the theory of fuzzy dark matter, and it proposes that the invisible stuff holding galaxies together isn't made of heavy bullets, but of an unimaginably vast number of particles so light that their quantum nature, their inherent waviness, becomes the dominant feature on the scale of entire galaxies. Imagine a single particle with a mass billions of times smaller than even the tiny electron, a featherweight so insignificant that it would take trillions upon trillions of them to equal the mass of a single gram. At this scale, the rules of the quantum world reign supreme. According to quantum mechanics, every particle has a wave-like character, and the wavelength of that wave is inversely proportional to the particle's mass. For a heavy particle like a proton, this wavelength is fantastically small, confined to the realm of the atomic nucleus. But for an ultra-light dark matter particle, this wavelength stretches out to a phenomenal size, potentially as large as a dwarf galaxy itself. Instead of a swarm of discrete points, this dark matter would behave like a single, coherent wave, a colossal quantum object enveloping entire galaxies in a standing wave of invisible matter. This is the fuzzy in fuzzy dark matter, not a collection of individual particles, but a smooth, wave-like fluid that fills the cosmos. The implications of this idea are profound and offer a potential solution to one of the most stubborn problems in modern cosmology, known as the missing satellites problem. For years, sophisticated computer simulations of the universe, based on the standard cold dark matter model, have predicted that our Milky Way galaxy should be surrounded by a very specific number of small, faint satellite galaxies. These simulations show a cosmos teeming with hundreds of these dark matter clumps, each a potential host for a tiny galaxy. Yet, when astronomers actually count the number of small satellite galaxies orbiting our Milky Way, they find far fewer than the simulations predict. It's as if the universe built a gigantic cosmic apartment building, but only a handful of the rooms are actually occupied. This discrepancy has been a major source of tension between theory and observation. Fuzzy dark matter provides an elegant way to resolve this tension. The reason lies in the unique physics of wave-like matter. In the early universe, as dark matter began to clump together under gravity to form the first structures, its wave-like nature would have imposed a fundamental limit. Waves exhibit a phenomenon called interference, where the peaks and troughs of waves overlap. They can either reinforce each other or cancel each other out. For fuzzy dark matter, this interference creates a natural minimum scale for clumping. Structures smaller than the particle's quantum wavelength simply cannot form because the waves would interfere destructively, smoothing out any tiny, dense lumps before they could collapse. This would effectively erase the smallest dark matter halos from the cosmic menu. If the quantum wavelength of fuzzy dark matter is on the scale of a few hundred light-years, it would naturally suppress the formation of the very smallest satellite galaxies, leaving behind only the larger ones, which aligns beautifully with the observed population around the Milky Way. We wouldn't expect to see hundreds of tiny satellites because the dark matter itself prevents them from ever forming in the first place. This theory also makes a striking prediction about the very centers of galaxies. In the standard cold dark matter model, the dense cusps predicted at the hearts of galaxies have been difficult to reconcile with observations, as we discussed with self-interacting dark matter. Fuzzy dark matter offers another solution. The wave nature of this material means it cannot be compressed into an infinitely sharp peak. Instead, it naturally forms a soft, flat core at the center of every dark matter halo, again matching what astronomers see in many dwarf galaxies without needing any additional interactions. The search for evidence of this cosmic wave is pushing the limits of astrophysical observation. One key method involves studying the thin, delicate streams of stars that orbit our galaxy. These streams are formed when a small star cluster or dwarf galaxy is torn apart by the Milky Way's gravity, leaving a long stellar ribbon winding through the halo. If dark matter is fuzzy and forms a wave-like halo, its granular, interference-driven structure would gravitationally perturb these streams, causing them to develop gaps and kinks that would be visible with powerful telescopes like the Vera C. Rubin Observatory, another approach, looks to the distant universe and the cosmic web itself. The distribution of gas and galaxies on the largest scales carries an imprint of the properties of the dark matter that shaped it. By mapping the universe in incredible detail, astronomers can look for the specific signature of a suppression of small-scale structure that would point directly to a fuzzy dark matter universe. While the action is also an ultralight candidate, fuzzy dark matter typically refers to particles at the very extreme end of lightness, where their wave-like behavior is the single most important factor determining the structure of the cosmos. It's a theory that replaces a sea of invisible particles with an ocean of invisible waves, a fundamental reimagining of the dark universe that suggests the solution to one of physics' greatest mysteries may not be a thing but a vibration. We've been exploring individual particles and specific theories, but what if all these disparate ideas, the WIMP, the actions, the gravitons, are just different facets of a single underlying reality? This brings us to one of the most ambitious intellectual frameworks ever conceived, a candidate for the long-sought theory of everything, and it fundamentally requires the existence of hidden dimensions. This is the world of string theory. At its heart, string theory proposes a radical departure from the standard model of particle physics. It suggests that the fundamental constituents of the universe are not zero-dimensional points, but unimaginably tiny, vibrating loops of energy strings. These strings are so small that if an atom were enlarged to the size of our solar system, a string would still be no larger than a tree on Earth. The different ways these strings vibrate, much like the different resonant notes on a guitar string, determine their properties. One specific vibrational pattern might correspond to an electron, another to a quark, and yet another to a photon. In this elegant picture, every particle and every force carrier in the universe is simply a different mode of vibration of the same fundamental string. But for this beautiful mathematical symphony to work, for the equations to balance and produce the universe we observe, string theory makes a breathtaking prediction. The fabric of our universe must have more than the three spatial dimensions we experience. It requires extra spatial dimensions curled up and compactified on a scale so minute that they are completely hidden from our everyday perception. Think of a long, thin garden hose. From a great distance, it appears to be a simple one-dimensional line, but if you get very close, you discover its two-dimensional surface curled into a cylinder. In an analogous way, string theory suggests that at every single point in our three-dimensional space, there exists a tiny, intricate, multi-dimensional shape. The properties of this shape, its geometry, its topology determine the possible vibrational notes of the strings that move through it, and therefore they determine the laws of physics themselves. The mass of an electron, the strength of gravity, the very existence of the different fundamental forces, all become consequences of the geometry of these hidden dimensions. This framework was later unified and expanded into what is known as M-theory, which proposes that there are actually 11 dimensions, and that the various string theories are all different limiting cases of this single master theory. In M-theory, the fundamental objects are not just one-dimensional strings, but also higher-dimensional membranes, or branes for short. Our entire visible universe could be a three-dimensional brane existing within a higher-dimensional bulk. This concept provides a stunningly elegant potential explanation for dark matter. What if dark matter is nothing more than ordinary matter that is stuck to a different brane? A parallel universe that occupies the same higher dimensional space as ours but is offset in an extra dimension. The particles of that other brane would be invisible to us because the photons of light, which are confined to our own brane, cannot jump across the gap to illuminate them. However, gravity, in many models, is different. It is a force generated by the fabric of space-time itself, and it can leak across all dimensions. So, while we could not see or touch the matter on this other brane, we would feel its gravitational pull. The missing 85% of the matter in the universe could simply be the matter of a parallel cosmic neighbor, whose presence we infer only through its ghostly gravitational shadow. Another compelling possibility within string theory is that dark matter is made of specific types of string vibrations that are sterile to the forces of our brane. Just as some vibrational patterns give rise to photons that interact with charged particles, other, more exotic patterns could give rise to particles that do not carry any charge under our standard model forces. These particles would be inert, feeling only gravity. They would have been produced copiously in the high-energy aftermath of the Big Bang and would now permeate the cosmos as a perfect dark matter candidate. The search for experimental evidence of these extra dimensions is one of the most thrilling challenges in modern physics. One approach involves using the world's most powerful particle accelerator, the Large Hadron Collider. If extra dimensions exist, they could allow for a remarkable phenomenon. When the LHC smashes protons together at nearly the speed of light, some of the energy of the collision could literally disappear into these hidden dimensions, carried away by gravitons that escape our brain. This would appear in detectors as an event where a significant amount of energy and momentum simply vanishes, a clear sign of physics beyond the standard model. Another method looks to the cosmos for signatures. The specific size and shape of the extra dimensions would influence how gravity behaves at extremely small distances. Exquisitely sensitive tabletop experiments are now testing Newton's law of gravity at scales smaller than a millimeter, searching for any deviation that would signal the presence of these compactified dimensions beginning to uncurl. While direct confirmation remains elusive, the profound power of string theory and M-theory is their ability to provide a unified home for so many of our isolated ideas about hidden particles. The action, the sterile neutrino, even the graviton itself, can all find a natural place within this multidimensional framework. It represents the ultimate promise of theoretical physics, that the bewildering complexity of the cosmos, from the whirl of galaxies to the buzz of the quantum world, emerges from the harmonious vibrations of fundamental strings dancing in the hidden, geometric heart of reality. This idea takes us from the hidden dimensions of string theory to a concept that is perhaps the most staggering of all, a framework where our entire universe, with all its laws and particles, is just one single bubble in an infinite cosmic foam. This is the theory of the multiverse, and its implications for the search for hidden particles are truly mind-bending. The journey to this conclusion often starts with the same cosmic inflation that gave us WIMPs. According to this theory, the universe underwent a period of hyper-fast expansion in its first fraction of a second. But what if this inflation isn't a one-time event that started and stopped? What if it's eternal, a process that continues forever in a vast background meta-universe? In this eternal picture, inflation doesn't end everywhere at once. Instead, pockets of space can randomly stop inflating and pop into a stable, low-energy state, each one becoming a separate, expanding universe like bubbles forming in a vast, boiling cauldron. Our entire cosmos, from the Big Bang to the present day, is just one such bubble, and crucially, when each bubble universe forms, the specific laws of physics that govern it are not preordained. They are randomly selected. Think of it like a cosmic lottery. The fundamental constants, the strength of gravity, the mass of the electron, the number of dimensions that uncurl to a macroscopic size, are not universal truths. They are simply the local bylaws of our particular bubble. In the wider multiverse, every possible combination of these constants is realized in some bubble universe somewhere. This has a direct and humbling consequence for our search for hidden particles. The specific set of particles we are desperately trying to find, the WIMP, the axions, the sterile neutrinos, may not be a necessary feature of reality. They might simply be a contingent feature of our universe's particular random draw from the cosmic hat. In another bubble universe, dark matter might be made of something we haven't even conceived of because the weak nuclear force there is stronger, or the Higgs field has a different value, making entirely different particle interactions possible. This concept is powerfully illustrated by the cosmological constant, the energy of empty space that is driving the accelerated expansion of our universe. Its observed value is extraordinarily small, yet from a theoretical standpoint, it should be a staggering 120 orders of magnitude larger. This is considered the worst fine-tuning problem in all of physics. The multiverse offers a stark, almost Copernican solution. There is no fine-tuning. In the vast majority of bubble universes, the cosmological constant is indeed enormous, and those universes expand so violently that galaxies, stars, and life never have a chance to form. We, of course, find ourselves in one of the exceedingly rare bubbles where the constant is small enough to allow for the emergence of complex structures and, ultimately, observers. This is known as the anthropic principle. We shouldn't be surprised to measure constants that allow for our existence, because in the universes where they don't, there's no one around to do the measuring. Apply this same logic to the hidden particles we've been discussing. The fact that dark matter in our universe seems to be stable, cold, and weakly interacting might not be a deep, fundamental truth. It might simply be a requirement for our own existence. If the dark matter particle were too unstable, it would have decayed away before galaxies could form. If it interacted too strongly, it would have smothered the formation of the first stars. We live in a universe where the dark matter has just the right properties to allow a galaxy like the Milky Way and a planet like Earth to exist. But that doesn't mean those are the only properties dark matter can have in the grand scheme of things. The multiverse theory transforms the quest for hidden particles from a hunt for universal truths into a form of cosmic archaeology. We are not discovering the one and only set of laws that govern reality. We are meticulously cataloging the local bylaws of our own cosmic neighborhood. Finding an action, for instance, would be a monumental discovery for us, but in the multiverse picture, it would tell us that in the cosmic lottery, our universe's number came up with a particular solution to the strong CP problem and a specific type of ultra-light dark matter. The universe next door might have solved it with a different mechanism altogether, and its dark matter might be something completely alien. This doesn't make the search any less meaningful. In fact, it makes it more profound. By identifying the specific hidden particles in our universe, we are essentially reading our own cosmic address. We are learning the unique identifier of our bubble in the infinite multiverse. Every experiment, from the deep underground detectors to the powerful particle colliders, is a step towards answering the question, out of all the possible universes that could exist, what kind of universe is ours? The multiverse suggests that the answers we seek are not written in stone for all of eternity, but are instead the local customs of our particular corner of a reality so vast and varied that it forever lies beyond the horizon of our own bubble, a perpetual reminder of the unending creativity of the cosmos. We've been exploring particles that might fill the cosmos, but what if the most fundamental hidden activity isn't from particles at all in the traditional sense, but from the very stage they perform on? This brings us to a concept that redefines the meaning of nothingness. According to quantum field theory, what we call empty space, the pure vacuum, is not a sterile, static void. It is instead a seething, turbulent ocean of energy, a place of constant, frantic activity. This isn't just a philosophical idea, it's a fundamental prediction of our most successful theories of the quantum world. At unimaginably tiny scales and over incredibly short time periods, the Heisenberg uncertainty principle allows for a temporary loan of energy from the universe. This energy is used to spontaneously create particle-antiparticle pairs, an electron and a positron, or a quark and an antiquark, which flicker into existence and then almost immediately annihilate each other, returning the energy loan before the universe at large can notice the debt. This endless, dizzying dance of creation and destruction means that every cubic centimeter of what you think of as empty space, including the space inside your own body, is a bubbling foam of these virtual particles. They are called virtual not because they aren't real, but because they are transient, unseeable guests at the cosmic party, their existence inferred only by the profound effects they leave behind. One of the most beautiful and direct demonstrations of this quantum frenzy is the Casimir effect. Imagine you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a perfect vacuum, only a few millionths of a meter apart. Classically, with nothing between them, you'd expect nothing to happen. But in our quantum reality, something remarkable occurs. The space between the plates is so narrow that only virtual particles with certain specific wavelengths can pop into existence there. The wider space outside the plates, however, allows for virtual particles of all wavelengths to appear. This creates a pressure imbalance, There are simply more virtual particles pushing on the outside of the plates than there are pushing on the inside. The result, the two plates are gently but measurably pulled together by the sheer pressure of this quantum foam. It's a force born from nothingness, a literal handshake from the hidden world of virtual particles that confirms the vacuum is alive with energy. An even more dramatic consequence of this vacuum activity arises from the work of Stephen Hawking, who applied quantum theory to the most extreme gravitational environment imaginable, a black hole. Just outside a black hole's event horizon, the point of no return, the gravitational field is unimaginably strong. Here, Hawking realized the virtual particle pairs popping out of the vacuum can be torn apart by this ferocious gravity before they have a chance to annihilate. Sometimes one particle of the pair falls into the black hole while the other escapes into space. From the perspective of a distant observer, the black hole has just emitted a particle. This is Hawking radiation. The particle that falls in has negative energy, which causes the black hole to lose a tiny amount of mass. Over astronomical timescales, this process causes black holes to slowly evaporate. Hawking radiation directly links the quantum weirdness of virtual particles to the physics of gravity, showing that even the vacuum itself is a player in the life cycle of the most mysterious objects in the universe. But this vibrant picture of the quantum vacuum leads us to one of the greatest puzzles in all of modern physics, a puzzle that brings us back to the largest scales of the cosmos. If empty space is teeming with this zero-point energy, this energy of the vacuum, then it should have a gravitational effect. According to Einstein's general relativity, all energy gravitates, and the energy density of the vacuum should manifest as a kind of repulsive gravity, an anti-gravity force that pushes the universe apart. This is in fact what we observe. We call it dark energy, the mysterious force driving the accelerated expansion of the universe. The problem, and it is a colossal one, is one of scale. When physicists calculate the theoretical energy density of the quantum vacuum based on our known particle physics, the number they get is wrong by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst theoretical prediction in the history of science. The vacuum energy should be so unimaginably powerful that it would have ripped our universe to shreds in the first instant of the Big Bang, preventing galaxies, stars, or life from ever forming. The fact that we exist and that we measure a much smaller value for dark energy means something is profoundly wrong or missing in our understanding. This is the cosmological constant problem. Is dark energy simply the energy of the quantum vacuum? If so, why is its value so infinitesimally small compared to our calculations? Or is there some other, yet unknown mechanism that is cancelling out almost all of this vacuum energy, leaving behind only the faint whisper we detect as dark energy? Some theorists propose that there may be a hidden symmetry or a new principle of physics that forces the vacuum energy to be exactly zero, and that dark energy is something else entirely, perhaps a dynamic field that slowly changes over time. Others suggest that the multitude of possible vacuum states in the string theory landscape of the multiverse means that we simply live in a universe where this cancellation, while not perfect, is very good, just good enough for us to exist. The mystery of the vacuum and its virtual particles, therefore, sits at the heart of two of the universe's biggest secrets, the behavior of black holes and the ultimate fate of the cosmos. It forces us to confront the possibility that the true nature of dark energy is inextricably linked to this seething quantum foam, and that solving one of the greatest puzzles of the very large may require a complete understanding of the very small. Now we turn our attention to a concept that pushes the very limits of physics into the realm of the truly surreal, a particle that would not just break the rules but shatter the entire rulebook. This is the tachyon, a hypothetical particle that, by its very nature, must always travel faster than the speed of light. The name itself comes from the Greek word tachys, meaning swift, and it represents an idea that is as intoxicating as it is problematic. You've likely heard that nothing can travel faster than light. It's one of the foundational pillars of Einstein's special theory of relativity. This cosmic speed limit isn't just about engines and power, it's woven into the very geometry of spacetime. As an object with mass accelerates, its energy increases, and according to relativity, so does its effective mass. To actually reach the speed of light would require an infinite amount of energy, an obvious impossibility for any object with real positive mass. Tachyons sidestep this entire problem in the most bizarre way imaginable. The theory suggests that these particles don't need to accelerate to reach superluminal speeds. They are born moving faster than light and can never slow down to the speed of light or below it. For them, the light-speed barrier is not a ceiling to be reached, but a floor they cannot fall below. How is this possible? The mathematical answer is as strange as the concept itself. In the equations, for a tachyon to have real energy and momentum, its mass squared must be a negative number. Since the square of a real number is always positive, this implies that the mass itself must be an imaginary number, a concept that exists in the abstract world of mathematics, where the square root of -1 is defined. This imaginary mass doesn't mean the particle is a fantasy. It's a formal way of saying its properties are inverted relative to ordinary matter, locking it into a perpetual state of faster-than-light travel. The allure of tachyons has made them a staple of science fiction for decades, often used as a convenient plot device for everything from instant communication across star systems to time travel itself. They represent the ultimate shortcut, a way to bypass the vast, lonely distances between stars that otherwise confine slower-than-light civilizations. But moving beyond fiction, the real-world implications of their existence would be far more disruptive, challenging our most fundamental understanding of cause and effect. The central problem is causality, the principle that a cause must always precede its effect. This isn't just a philosophical notion, it's the logical foundation upon which all of physics is built. If tachyons were real and could be used to transmit information, they could potentially create scenarios where an observer in a different state of motion would perceive the effect happening before the cause. Imagine a tachyon-based message sent from Earth to a distant planet. Due to the weird way time and space mix at superluminal speeds in relativity, there could be a perfectly valid reference frame from which that message arrives at the planet before it was even sent from Earth. This opens the door to infamous paradoxes like the grandfather paradox, where you could theoretically send a signal back in time to prevent your own birth. Most physicists view this as a fatal flaw, a strong indication that the universe fundamentally prohibits such backwards in-time signaling to preserve a consistent and logical flow of time. The prevailing scientific opinion is that if tachyons exist at all, they are likely entirely undetectable, incapable of carrying information or interacting with ordinary matter in any measurable way. They would be phantoms in the equations, having no causal connection to our world, and thus posing no threat to the established order of spacetime. Despite the profound skepticism, the hunt for any faint signature of these particles has not been entirely abandoned. If tachyons exist, one proposed method of detection involves looking for a unique form of radiation they might emit, known as Cherenkov radiation for tachyons. You might be familiar with ordinary Cherenkov radiation, that beautiful, eerie blue glow seen in the water surrounding a nuclear reactor. It occurs when a charged particle, like an electron, travels through a medium like water faster than light can travel in that same medium. It's a luminous sonic boom for light. A tachyon, by definition, travels faster than light in a vacuum, the ultimate cosmic speed limit. Therefore, if a charged tachyon were to pass through any medium, even empty space with its faint quantum fields, it should, in theory, lose energy by emitting a unique form of this radiation across a broad spectrum. Astronomers have occasionally scanned the heavens for any unexplained broadband radiation that could fit this description, but so far, no convincing evidence has ever been found. The continued absence of any such signal further deepens the conviction that tachyons are a mathematical curiosity rather than a physical reality. Yet, the idea remains tantalizing because it forces us to confront the boundaries of our knowledge. The fact that special relativity can be mathematically extended to accommodate particles with imaginary mass tells us that our models have edges, places where the logic of the universe as we know it begins to fray. Exploring these edges, even when the conclusions point towards impossibility, is a vital part of theoretical physics. It defines the frontier, reminding us that our current understanding, however successful, may not be the final word. The tachyon stands as a ghost at the edge of physics, a symbol of what might be possible if the most sacred rules were broken, and a testament to the human imagination's relentless drive to explore even the most forbidden territories of reality. But what if the fundamental particles we've discovered so far, the quarks and electrons that form the bedrock of all visible matter, are not truly fundamental at all? This brings us to a theory that challenges the very foundations of the Standard Model, a proposal that the universe's building blocks are even smaller and more elusive. This is the world of prions, hypothetical subcomponents that could make up the quarks and leptons we thought were indivisible. For decades, the triumph of particle physics has been the identification of this particle zoo. 6 types of quarks, the electron and its heavier cousins, and the ghostly neutrinos. The Standard Model treats these as point-like, fundamental entities with no internal structure. But to some theorists, this sprawling family of particles feels less like a set of fundamental building blocks and more like a periodic table, hinting at a deeper, more elegant level of reality beneath the surface. The prion model was born from this desire for a more unified picture. Why are there 3 generations of matter, each a heavier copy of the first? Why do the particles have the specific masses and charges they do? The prion theory proposes that all quarks and leptons are actually different combinations of a very small number of these more primitive entities. Imagine the known particles are like words, and prions are the letters of a cosmic alphabet. By arranging just a few different types of prions in various ways, you could potentially spell out every single particle in the Standard Model, from the up quark to the tau neutrino. This would represent an incredible simplification, reducing the dizzying complexity of the particle zoo to a handful of truly fundamental objects and the rules that govern their combinations. The appeal is immense. It could explain the patterns and symmetries we see in particle properties as natural consequences of this underlying prion structure. The different electric charges of particles would no longer be arbitrary numbers assigned by nature, but would emerge from the specific combination of charged prions that form them. The replication across 3 generations could be understood as different vibrational or orbital states of the same prion constituents. This model offers a breathtakingly elegant vision of a universe built from a very small set of ultimate Lego bricks. However, this beautiful idea runs into formidable theoretical and experimental challenges. The most significant puzzle is the issue of binding energy. The protons and neutrons in atomic nuclei are bound together by the strong nuclear force, and the energy associated with that binding is what gives them most of their mass, as described by Einstein's famous equation. Now, if quarks themselves are made of prions held together by some new, even more powerful force, the energy required to confine them would be astronomical. This binding energy would contribute to the mass of the quark in a way that should make it incredibly heavy, far heavier than what we actually observe. Reconciling the relatively light masses of quarks and electrons with the idea that they are composite objects made of constituents bound by a tremendous force is a major hurdle for prion models. It requires a delicate and unnatural cancellation of effects that has so far eluded a convincing theoretical solution. Then there is the experimental evidence, or rather, the lack thereof. We probe the structure of particles by firing other particles at them at incredibly high speeds, much like using a powerful microscope. The Large Hadron Collider is the most powerful microscope ever built, capable of resolving details down to about 1,000th the size of a proton. If quarks or electrons had any internal structure at the scale the LHC can probe, we would expect to see signs of it in the debris of high-energy collisions. We would look for excited states of these particles' temporary, higher-energy configurations of their prion components, or for evidence that they can be broken apart. So far, every electron and every quark has behaved as a perfect, point-like particle at the resolution of our experiments. They have shown no hint of having any parts to smash open. This doesn't rule out prions entirely, but it pushes their possible size to a scale far smaller than we can currently access, suggesting that if they exist, the energy required to see them is far beyond the reach of any collider we could envision building in the foreseeable future. Yet the dream persists because the payoff would be nothing less than a second scientific revolution in particle physics. Discovering that quarks and leptons are composite would shatter the standard model as a theory of fundamental particles. It would open up a vast new frontier, a whole new layer of reality to explore. We would have to discover the new force that binds prions together, a force far stronger than the strong nuclear force we currently know. We would need to understand the laws that govern this hidden realm. The identification of prions would be akin to discovering that the atom, once thought to be indivisible, was actually composed of a nucleus and orbiting electrons. It would not be the end of physics, but a glorious new beginning, revealing a sub-quark world with its own unique rules and dynamics, and potentially offering answers to questions we have not yet even learned how to ask. Now, let's explore one of the most abstract and mind-bending ideas on the frontier of theoretical physics, a concept that challenges our very definition of what a particle is. This is the theory of unparticle physics. Imagine if you could take a particle and somehow strip it of its defining characteristic, its mass. Without mass, the familiar link between a particle's energy and its momentum is broken. It no longer fits into the neat categories we have for the particles of the standard model. Unparticle physics proposes the existence of an entire sector of reality, a hidden world of fields and forces that operates under a completely different set of rules. This unparticle sector is theorized to be scale invariant, which is a sophisticated way of saying it has no intrinsic scale or size. It looks the same and behaves the same, whether you're observing it at the scale of a galaxy or the scale of an atomic nucleus. In our everyday world, scale matters tremendously. The forces that hold a molecule together are completely different from the forces that govern planetary orbits. But in a scale-invariant system, this hierarchy vanishes. There is no preferred size, no fundamental unit. The theory suggests that in the extremely high-energy environment of the early universe, this unparticle sector interacted with our familiar standard model particles through the exchange of very heavy messenger particles. As the universe cooled and expanded, a phase transition occurred, causing this unparticle sector to decouple and become what physicists call a Banks-Zaks sector, a hidden realm with its own unique scale-invariant behavior. The most profound consequence of this is how unparticle stuff would manifest in experiments. It wouldn't behave like a collection of discrete particles. You couldn't count individual unparticles because the concept of a single, countable entity doesn't apply. Instead, this hidden substance would act more like a continuous, ethereal fluid. When a particle collision in an accelerator produces unparticles, it wouldn't create a specific particle with a specific mass. It would produce a cloud of this scale-invariant stuff, a continuum of states that carries away energy and momentum in a very strange, smeared-out way. This leads to one of the most tantalizing and confusing possibilities for experimentalists. In a detector at a place like the Large Hadron Collider, the signature of unparticle production would be the appearance of missing energy. When two protons collide, we meticulously account for all the energy and momentum of the resulting debris. If a significant amount of energy simply vanishes, carried away by something the detector cannot see, it's a classic signature of new physics, and the prime suspect is often dark matter. But unparticles would create a very particular kind of missing energy signature. Unlike a WIMP, which would leave a clean, single spike of missing energy corresponding to its mass, unparticles would produce a broad, continuous spectrum of missing energy. It would look less like a single ghost passing through the detector and more like a diffuse, invisible fog seeping away with the energy of the collision. This strange, continuous nature could lead physicists to misinterpret the data. They might see this unusual missing energy pattern and assume it's a complex form of dark matter, or perhaps an instrumental error, when in reality it could be the first glimpse of a scale-invariant hidden sector. The implications of discovering unparticles would be nothing short of revolutionary. It would mean that at a fundamental level, reality is not entirely quantized into discrete packets. A portion of the cosmos would operate on a continuum, behaving more like a classical field than a collection of quantum particles. This would force a profound rewrite of quantum field theory itself. Furthermore, because this unparticle sector interacts so weakly with ordinary matter, it becomes a perfect candidate for the dark matter that shapes the cosmos. Its continuous, fluid-like nature could even help explain some of the small-scale puzzles in galaxy formation, as its lack of discrete particles might suppress the formation of the tiniest dark matter clumps in a way that matches astronomical observations. The search for this ethereal substance is a testament to the creativity of modern physics, pushing us to consider that the hidden architecture of the universe may be far stranger and more beautiful than a simple collection of invisible particles. For all the ghostly subtlety of these individual candidates, their collective gravitational presence is unmistakable and colossal. The most powerful evidence for this hidden cosmos doesn't come from a single experiment on Earth, but from multiple, independent lines of astronomical observation that all point to the same astonishing conclusion. The universe is filled with an invisible mass that guides the formation and motion of everything we see. The first and perhaps most profound clue is etched into the oldest light in the universe, the cosmic microwave background. This is the remnant glow from the Big Bang, a snapshot of the universe when it was just 380,000 years old, a swirling sea of hot plasma. Tiny ripples in this plasma, imprinted by quantum fluctuations from the universe's first instant, were the seeds for all future structure. But the pattern of these ripples, mapped with exquisite precision by satellites like Planck, tells a very specific story about what that primordial plasma was made of. The size and distribution of the hot and cold spots reveal that ordinary matter, the protons, neutrons, and electrons that would become stars and galaxies, simply did not have enough gravitational pull by itself to create the structures we see today. The data requires a massive, additional ingredient that was gravitationally active but did not interact with light. This dark matter provided the necessary gravitational wells for the ordinary matter to fall into, accelerating the growth of galaxies and sculpting the large-scale cosmic web. Without this invisible scaffolding, the pattern of the cosmic microwave background would be completely different, and the universe would be a much smoother, far less interesting place. Moving from the infant universe to the galaxies we see today, a second line of evidence emerges from the way stars orbit their galactic centers. According to the laws of gravity, the speed at which stars and gas clouds revolve around a galaxy should decrease as you move further out from the core, just as the outer planets in our solar system orbit the Sun more slowly than the inner ones. But when astronomer Vera Rubin meticulously measured the rotation curves of spiral galaxies in the 1970s, she found something that defied this expectation. The orbital speeds of stars remained constant or even increased far out into the galactic outskirts. This was a monumental discovery. The only way this could happen is if the galaxies were embedded within enormous, massive halos of something invisible, a dark matter sphere whose gravitational influence keeps the outer stars whipping around at high speeds. We are not seeing the true extent of a galaxy when we look at its stars. We are merely seeing the bright tip of a vast, dark iceberg. The third and most dramatic demonstration comes from a phenomenon that acts as nature's own X-ray vision for mass, gravitational lensing. Einstein's theory of general relativity tells us that mass warps the fabric of spacetime, bending the path of light that travels near it. A massive object like a galaxy cluster can act as a cosmic lens, magnifying and distorting the images of galaxies that lie far behind it. By studying this distortion, astronomers can literally map the distribution of all mass in the foreground cluster, both visible and invisible. The results are staggering. In colossal collisions of galaxy clusters like the famous Bullet cluster, the maps reveal a clear separation. The hot, X-ray emitting gas, the bulk of the ordinary matter, slams into itself and gets stuck in the middle of the collision. But the total mass, as revealed by the gravitational lensing map, has sailed right through the crash site, perfectly aligned with the locations of the galaxies themselves. This proves, in the most direct way possible, that most of the matter is not only dark, but it is also fundamentally different from the atomic matter we know. It doesn't slow down due to friction or collisions because it barely interacts with itself or anything else. It is the ghostly, gravitational skeleton of the cosmos, and we can trace its outline by watching how it bends the very light from distant galaxies. Together, these three pillars, the cosmic microwave background, galaxy rotation curves, and gravitational lensing, form an irrefutable case. They show us that dark matter is not a single, small component of the universe, but its dominant form of matter. It is the invisible architect that drew up the blueprints for the cosmic web in the first moments of time, the force that holds spinning galaxies together, and the phantom mass that reveals itself only by its relentless gravitational pull, guiding the evolution of everything from the largest galaxy clusters to the smallest dwarf galaxies. We have already met the neutrino, the cosmic ghost that can pass through light years of lead. But this known particle holds a secret so profound it could rewrite the story of our cosmic origins. For years, neutrinos presented a major puzzle. Why are they so incredibly light? The electron, the next lightest particle, is at least 1,000,000 times heavier than the heaviest neutrino. This staggering imbalance seemed arbitrary, a strange quirk of nature without a deeper explanation. The seesaw mechanism offers a breathtakingly elegant solution, and in doing so, it predicts the existence of a whole new class of hidden particles that could be the ultimate architects of our material universe. The name itself paints a perfect picture. Imagine a playground seesaw. On one end, you have a very light, familiar neutrino. On the other end, you have an unimaginably heavy, hypothetical neutrino. As one side goes down, the other must go up. The seesaw mechanism in physics works the same way. The incredible heaviness of a new particle is directly linked to the incredible lightness of the ordinary neutrinos we know and love. This new particle is the sterile neutrino we discussed earlier, but in its heaviest possible incarnation, a true behemoth. The mechanism works through a simple but powerful idea. All the neutrinos we have ever observed are left-handed, meaning their spin is oriented in a specific way relative to their direction of motion. According to our fundamental theories, for every left-handed particle, there should be a right-handed partner. For the electron, this partner is the positron, but for the neutrino, this right-handed partner has never been seen. The seesaw mechanism proposes that these right-handed neutrinos do exist, but they are fundamentally different. They are sterile, feeling none of the standard model forces, and they are monumentally heavy, potentially 1 trillion times heavier than a proton. The mathematics of this model show that the mass of the light, left-handed neutrino we observe is inversely proportional to the mass of its heavy, right-handed cousin. The heavier the sterile neutrino is, the lighter the ordinary neutrino becomes. This isn't just a clever trick, it's a natural outcome of the fields and symmetries involved. The seesaw provides a beautiful reason for the neutrino's featherweight status, transforming it from a puzzling anomaly into a predictable consequence of a much grander, hidden structure. But the implications of these heavy sterile neutrinos extend far beyond just explaining mass. They could be the key to solving one of the most fundamental mysteries of existence. Why is the universe made of matter at all? During the Big Bang, matter and antimatter should have been created in perfectly equal amounts. Yet when matter and antimatter meet, they annihilate each other in a flash of energy. If the initial balance had been perfect, all of existence would have annihilated into a sea of pure radiation, leaving behind a universe with no stars, no planets, and no us. The fact that we live in a cosmos dominated by matter means that some process in the early universe must have violated this perfect symmetry, creating a tiny 1 in a billion excess of matter over antimatter. This process is known as baryogenesis, the genesis of baryonic matter. The heavy sterile neutrino is a prime candidate for the particle that made this possible. Here is how it might have worked. In the seething, high-energy chaos of the very early universe, these heavy neutrinos would have been produced copiously. Because they are so massive and unstable, they would not have lasted long. They would have decayed. The crucial point is that the laws of physics, under certain conditions, allow for a phenomenon called CP violation, where a particle and its antiparticle decay at slightly different rates and into slightly different products. If these heavy sterile neutrinos decayed in a CP-violating way, they could have produced more matter particles than antimatter particles in their decay products. Imagine a hypothetical heavy neutrino decay. For every 1,000 decays that produce matter, only 999 might produce antimatter. This tiny 1 part in 1,000 imbalance is all that would be needed. After all the violent particle-antiparticle annihilations finished, this slight excess of matter would be all that remained, the raw material for every galaxy, star, and planet that would ever form. The light, everyday neutrinos we detect now would be the lightweight siblings left over from this cataclysmic process, the eternal, quiet reminder of their heavy relatives who, in their fleeting existence, tilted the cosmic scales and made a material universe possible. The hunt for evidence of this magnificent mechanism is underway on multiple fronts. Particle physicists are pushing for next-generation experiments to measure the properties of the known light neutrinos with even greater precision. If we can determine their exact masses and confirm that they are their own antiparticles, a property known as Majorana mass, it would be a powerful indirect hint that the seesaw mechanism is correct. Meanwhile, cosmologists are refining their models of the early universe, testing whether the decays of heavy sterile neutrinos could indeed produce the observed matter-antimatter asymmetry. The search is also on for the direct production of these heavy neutrinos, though their extraordinary mass puts them far beyond the reach of any current particle collider. The seesaw mechanism elegantly ties together three great mysteries: the neutrino's small mass, the existence of sterile neutrinos, and the origin of matter itself, into a single, compelling narrative, suggesting that the ghostly neutrinos passing through us are the faint echoes of their colossal ancestors, whose dramatic lives and deaths in the first moments of time ultimately set the stage. Everything we see, returning to the action, the particle we introduced earlier as a leading dark matter candidate, we must now explore the deep and puzzling mystery that first called it into existence. This isn't just a story about invisible matter, it's about a fundamental symmetry of nature that appears to be perfectly and inexplicably preserved. The puzzle is known as the strong CP problem, and to understand it, we need to look at the force that holds atomic nuclei together. The strong nuclear force is governed by a theory called quantum chromodynamics, or QCD, which describes how quarks are bound by gluons to form protons and neutrons. The mathematical equations of QCD contain a potential term that would allow for a violation of CP symmetry. Now, CP stands for charge and parity. A violation of this symmetry means that the laws of physics would treat particles and their mirror-image antimatter counterparts differently. We know CP violation happens in the weak nuclear force. It's a small effect, but it's crucial, as it's part of the reason we have a universe made of matter. However, in the immensely powerful strong nuclear force, this CP violating term should be enormous. Its presence would have dramatic, observable consequences. Most notably, it would cause the neutron, the neutral particle inside every atomic nucleus, to possess a tiny electric dipole moment. You can picture a neutron as a tiny, perfect sphere with a uniform distribution of positive and negative charges. If CP were violated in the strong force, this perfect symmetry would be broken. The neutron would have a slight positive charge shifted towards one end and a negative charge towards the other, like a microscopic battery. This electric dipole moment would be small, but it would be there. Physicists have searched for this effect with experiments of breathtaking sensitivity, isolating neutrons and probing them with incredibly precise electromagnetic fields. The result is definitive. The neutron's electric dipole moment is zero to an astonishing degree of precision. The strong force, against all theoretical expectation, perfectly respects CP symmetry. This presents a profound fine-tuning problem. The mathematical parameter that controls this CP violation, called theta, could theoretically take on any value. For the universe to look the way it does, with symmetrical neutrons and stable atoms, this theta parameter must be tuned to zero with an accuracy of 1 part in a billion. It's as if a dial with a huge range of possible settings was somehow set to exactly zero, and we have no idea why. This arbitrary, perfect cancellation makes physicists deeply uncomfortable. It feels like a cosmic coincidence begging for a deeper explanation. This is where the action enters the stage, not as a dark matter candidate first, but as a savior of cosmic symmetry. In 1977, physicists Roberto Pexi and Helen Quinn proposed an elegant solution. They suggested that this theta parameter is not a fixed fundamental constant, but is actually a dynamic field that can relax to its natural, lowest energy state. Think of it like a ball sitting on a sloped surface. It will always roll down to the bottom. In the Pexi-Quinn theory, the universe naturally rolls to the state where the CP violating term is zero. The act of this field settling to its minimum value, however, has a physical consequence. Just as the Higgs field has an associated particle, the Higgs boson, this new field also produces a particle, a light, weakly interacting scalar particle. This particle was named the action. The action is the ripple in this new cosmic field, and its existence forces the strong force to behave with the perfect symmetry we observe. The problem is solved not by fine-tuning, but by the dynamics of a new fundamental component of reality. What's truly stunning is that this particle, invented to solve an obscure problem in nuclear physics, turned out to have all the right properties to be the dark matter that permeates the cosmos. It was a convergence of two seemingly unrelated puzzles into one beautiful solution. But the story doesn't end with the classic action. The elegance of this mechanism has led physicists to consider a broader class of possibilities known as action-like particles, or ALP. While the original action's properties are tightly linked to the specifics of the strong CP problem, ALPs are its more versatile cousins. They arise in a wide variety of theoretical frameworks, particularly in string theory, where they are often associated with the geometry of the extra dimensions we discussed earlier. The key difference is that for ALPs, the relationship between their mass and their interaction strength is more flexible. An ALP could be much lighter or much heavier than the classic QCD action, and it could couple to different forces, not just to the strong nuclear force. Some ALPs might interact predominantly with photons, for instance. This opens up a vast and varied landscape for discovery. The search for these particles has therefore expanded into a multi-pronged assault on the hidden universe. Since many ALPs could convert to and from photons in the presence of a magnetic field, one major approach is to use powerful magnets as a kind of action-to-light converter. Experiments like the Any Light Particle Search, or ALPS, use a strong magnetic field in front of a wall to convert photons from a laser into ALPs. These ALPs would then pass through the wall, as ordinary matter is transparent to them, into another magnetic field on the other side, where a tiny fraction would reconvert back into photons, appearing in a detector as if they had passed through the solid barrier. It's a search for light shining through a wall, a seemingly magical effect that would be a clear sign of a new, hidden particle. Other searches are cosmological. If ALPs make up dark matter, they could decay, albeit very slowly, into pairs of photons. Astronomers scan the X-ray and gamma-ray spectra of galaxy clusters, looking for an unexpected, diffuse emission line at a specific energy that could be the collective glow of decaying ALPs. The flexibility of the ALP concept means that the hunt is on across a huge range of possible masses and interaction strengths. From particles so light they behave as a pervasive wave to others that are heavy enough to be detected in particle colliders. The pursuit of the action and its cousins is a perfect example of how theoretical beauty can guide experimental science. It began with a deep puzzle in the heart of the atom, led to a hypothetical particle that restored cosmic symmetry, and ultimately opened a window into the dark sector of the universe, revealing a family of hidden particles whose discovery would illuminate not only what holds galaxies together, but also the deepest, most symmetric principles that govern the forces binding our reality. But for all the complexity of our particle zoo, what if it represents only a fraction of what's truly out there? This brings us to a profoundly simple yet radical idea: the existence of a completely hidden sector of particles, an entire universe of matter and forces operating in parallel to our own, forever invisible and untouched by the familiar forces of electromagnetism and the strong and weak nuclear interactions. This hidden sector could have its own particles, its own atoms, and even its own complex structures, all completely isolated from us. The only possible bridge between our world and this shadow realm, the only conceivable portal, might be the most famous particle of the 21st century, the Higgs boson. You see, the Higgs field is unique. It's the only fundamental scalar field in the Standard Model, a field that has a non-zero value everywhere in space, even in a perfect vacuum. It's this omnipresent field that gives mass to fundamental particles like electrons and quarks. Because the Higgs field is everywhere and interacts with so much, it becomes the perfect candidate for a cosmic messenger, a potential gateway to the hidden world. This concept is known as the Higgs portal. The theory is elegantly straightforward. It proposes that the Higgs field of our Standard Model could mix or interact with a hypothetical Higgs-like field from the hidden sector. This mixing would be incredibly faint, a whisper of a connection, but it would be enough to tear a tiny hole in the wall separating the two realities. Through this Higgs portal, particles from our world could, under very specific and rare conditions, communicate with or even transform into particles from the hidden sector. The implications for detection are thrilling. At a massive particle collider like the Large Hadron Collider, scientists routinely smash protons together at incredible speeds, recreating the energetic conditions of the early universe. One of the primary goals is to produce and study the Higgs boson, which is essentially an excitation or a ripple in the omnipresent Higgs field. If the Higgs portal is real, then occasionally, when a Higgs boson is created in these violent collisions, it might not decay into the usual assortment of bottom quarks and photons that we expect. Instead, it could oscillate or decay into hidden sector particles. From the perspective of the giant detectors like ATLAS and CMS, this would be a truly bizarre event. They would see all the initial energy and momentum of the colliding protons, and they would confirm that a Higgs boson was produced, but then the Higgs would simply vanish. It would disappear without a trace, leaving behind no detectable debris in the detector. This signature is known as invisible decay, and it would manifest as a significant, inexplicable amount of missing energy. Researchers are meticulously searching for exactly this, sifting through billions of collision events, looking for the telltale sign of a Higgs boson seemingly evaporating into thin air, its mass and energy carried away by invisible particles escaping the detector. But the hidden sector could reveal itself in another, even more intriguing way. The interaction through the Higgs portal might not just allow our Higgs to decay into hidden particles, it could also allow those hidden particles to decay back into our visible world. Imagine a scenario where a Higgs boson produced at the LHC decays into a pair of hidden sector particles. These phantoms would then fly away undetected. But if those hidden particles are unstable, they might not live forever. After a short time, they could themselves decay, and if that decay chain ultimately leads back to standard model particles, we could witness a truly mysterious event. The detector would see a pair of particles, like electrons or muons, suddenly appearing out of nowhere with no visible parent particle to explain their origin. It would look like matter materializing spontaneously from empty space, a ghostly echo from the hidden sector. Beyond the controlled environment of particle colliders, the Higgs portal could also solve a major cosmological puzzle. If the hidden sector exists, it almost certainly contains its own form of dark matter. A hidden sector particle could be stable, neutral, and interact with our world only through its minuscule coupling to the Higgs field. This would make it an excellent candidate for the missing mass in the universe. In this model, dark matter particles would rarely, but occasionally, bump into the nuclei of ordinary atoms through the exchange of a virtual Higgs boson. This interaction would be exquisitely weak, making these particles incredibly difficult to detect in underground experiments, but it provides a clear, testable target for the next generation of ultra-sensitive detectors. The beauty of the Higgs portal hypothesis is its minimalism. It doesn't require a complete overhaul of physics. It simply adds one small, fragile bridge between our known world and a vast, unknown one. Discovering evidence for this portal would be like finding a secret door in a house you've lived in your entire life, a door leading to rooms you never knew existed. It would redefine the Higgs boson not just as the particle that gives us mass, but as the cosmic custodian of a hidden universe, the one and only key to a realm of shadow particles that have been living alongside us, completely undetected since the very beginning of time. While the discovery of the Higgs boson in 2012 was a monumental triumph, confirming the final piece of the Standard Model, it also presented a new set of puzzles that sent theorists back to their drawing boards. Why is the Higgs boson so relatively light, and why does it seem to be a lone, elementary particle in a class of its own? These questions open the door for a fascinating and radical alternative to the standard Higgs mechanism, a class of theories known as technicolor. This framework completely reimagines the nature of the Higgs boson itself, proposing that it is not a fundamental particle at all, but a composite object, a bound state of entirely new constituents. Imagine the proton in the nucleus of an atom. We know it's not elementary, it's made of three quarks held together by the strong nuclear force. Technicolor theories suggest the Higgs boson is analogous, a tiny composite ball held together by a new, powerful force. The constituents of this Higgs composite are hypothetical particles called techni-fermions, and the force that binds them is a new, strong interaction analogous to the force that binds quarks, hence the name technicolor. In this picture, the act of giving mass to other particles isn't accomplished by a fundamental Higgs field, but by the dynamics of this new, strongly interacting techni world. The process is akin to superconductivity, where the collective behavior of many electrons leads to the expulsion of magnetic fields. In the Technicolor universe, the condensate of technifermions filling space breaks the electroweak symmetry, effectively giving mass to the W and Z bosons and the other fundamental particles, all without the need for a fundamental Higgs field. This was an incredibly elegant and attractive idea because it solved the so-called hierarchy problem naturally. In the Standard Model, the Higgs mass is vulnerable to enormous quantum corrections that should make it astronomically heavy, requiring an unnatural fine-tuning to keep it light. But in composite models, the Higgs is light because it is a composite particle, and its mass is protected by its size, just as the proton's mass is stable and not driven to enormous values by quantum effects. The Higgs, in this view, is like a pion in the strong force, a relatively light composite particle emerging from a much stronger, high-energy interaction. The implications of this hidden technisector extend far beyond just explaining the origin of mass. This entire universe of techniparticles, with its own forces and dynamics, could have produced a perfect candidate for dark matter. A stable, neutral technibaryon, analogous to the neutron in our visible world, could have been forged in the early universe. This particle would be massive and interact only very weakly with ordinary matter, primarily through the Higgs portal or residual techniforce effects, making it an excellent cold dark matter candidate. Its gravitational influence would be exactly what we observe holding galaxies together, meaning the same hidden physics that gives particles their mass could also account for the universe's missing matter. For decades, Technicolor was a leading contender for physics beyond the Standard Model. However, the actual discovery of the Higgs boson at the Large Hadron Collider dealt a severe blow to the simplest and most elegant versions of these theories. The Higgs that was found has properties that are, so far, strikingly consistent with the predictions of a fundamental, elementary Standard Model Higgs boson. Its mass, its spin of zero, and the way it couples to other particles all align beautifully with the simple picture. The most straightforward Technicolor models, on the other hand, predicted significant deviations from this behavior. They tended to forecast a Higgs-like particle that was either much heavier or one that had different interaction strengths, particularly with the massive W and Z bosons. The data from the LHC has shown no such deviations. The Higgs appears to be vanilla, behaving almost exactly as the Standard Model says it should. Furthermore, these simple Technicolor models also predicted a whole host of other new composite particles, techni-mesons and techni-baryons, that should have been within the energy reach of the LHC. Extensive searches for these resonances have, to date, come up empty. The absence of these partner particles has forced the physics community to largely set aside the most minimal Technicolor constructions. Yet the core idea is so compelling that it has evolved rather than died out. Modern incarnations, such as composite Higgs models and theories with partial compositeness, have incorporated the lessons from the LHC data. In these more sophisticated frameworks, the Higgs boson is still a composite particle, but it is a special, light state emerging from a strongly interacting sector that exists at a much higher energy scale. This makes its Standard Model-like behavior a natural outcome rather than a contradiction. These models often predict that the Higgs has subtle deviations in its properties that will only become apparent with more precise measurements, and they still predict a rich spectrum of new particles, though at energies that may be beyond the current reach of the LHC. The story of Technicolor is a powerful lesson in how science progresses through a dialogue between bold theoretical imagination and uncompromising experimental data. It represents a breathtakingly different vision of reality, one where the Higgs boson is not a fundamental entity but a glimpse into a deeper, more complex layer of strong interactions governing the cosmos. While the simplest map of this hidden techni-world has been rolled up, the territory it sought to describe remains a compelling frontier, driving the quest for the next generation of particle accelerators that might finally reveal the true composite nature of the cosmic architecture. Now, let's journey into one of the most mind-bending conflicts in all of physics, a paradox that pits our understanding of quantum mechanics directly against Einstein's theory of gravity and suggests a violent, hidden reality at the edge of a black hole. This is the black hole information paradox and its proposed resolution, the firewall hypothesis, which paints a picture far more dramatic than the serene black holes we often imagine. To understand the paradox, you first need to grasp two principles that physicists hold sacred. The first is the no-drama principle of general relativity. If you were to fall into a black hole, Einstein's equations suggest you would cross the event horizon, the point of no return, without noticing anything special at all. There would be no signpost, no sudden jolt. It would be a smooth, uneventful crossing into the interior, at least until the tidal forces eventually pulled you apart. The second sacred principle is from quantum mechanics, the law of information conservation. In the quantum world, information is never truly lost. If you burn a book, the information in its pages seems to be destroyed, but in reality, it's just scrambled into the heat, light, and smoke. In principle, with a perfect, impossibly powerful computer, you could reverse the process and reconstruct the book from its ashes. Every particle interaction is reversible, information is always preserved. The paradox arises when these two cherished principles collide at a black hole. In the 1970s, Stephen Hawking made a revolutionary discovery: black holes are not completely black. Due to quantum effects at the event horizon, they slowly emit radiation and evaporate over astronomical timescales. This Hawking radiation, however, presents a catastrophic problem. Hawking's original calculations showed that this radiation is purely thermal, like the glow from a hot piece of coal. It contains no information about what fell into the black hole. It is random noise, so imagine you throw a specific, information-rich object into a black hole, say, a diamond, a computer, or a book. According to Hawking, after the black hole has completely evaporated via this thermal radiation, all that remains is a featureless cloud of heat. The specific quantum information that described the unique arrangement of particles in your diamond has been lost forever. This violates the core tenet of quantum mechanics. The information is gone, and the universe has seemingly forgotten what fell in. For decades, this was the central puzzle. Does general relativity's peaceful entry win, allowing information to be lost inside, or does quantum mechanics win, demanding information must somehow escape? Most physicists sided with quantum mechanics, believing a deeper theory must resolve the paradox and preserve information. The leading idea for years was quantum complementarity, which suggested that from the perspective of someone outside the black hole, the information never actually crosses the horizon but is smeared onto it, while for someone falling in, it does cross smoothly. It was a clever, if subtle, workaround. But in 2012, a team of physicists unveiled a far more radical and violent solution: the firewall. They argued that the gentle compromises didn't work. To save quantum mechanics and ensure information isn't lost, you must sacrifice the no-drama principle of general relativity. Their conclusion was stunning. They proposed that the event horizon is not a peaceful place at all. Instead, it is a searing, energetic boundary, a literal firewall. An infalling observer wouldn't experience a smooth crossing. They would be instantly incinerated by a wall of unimaginably high energy particles the moment they reached the event horizon. The black hole's surface would be a destructive inferno. This idea sent shockwaves through the theoretical physics community. What could this firewall be made of? Is it a new, exotic form of matter, a previously unknown state of energy that only exists under these most extreme gravitational conditions? Or is it not a substance at all, but a manifestation of the violent clash between the two great pillars of physics? The firewall could be the physical signature of quantum mechanics and general relativity engaging in a fundamental conflict. a region where space-time itself becomes so stressed that it breaks down into a turbulent sea of its most basic constituents. In this view, the smooth, continuous space-time described by Einstein ceases to exist at the horizon, replaced by a chaotic, discrete foam of quantum gravity, where every Planck-scale area buzzes with incredible energy. This firewall would be composed of every possible particle and antiparticle existing in a state of extreme excitation, a tangible and lethal barrier encoding the information of everything that ever fell into the black hole. It's as if the black hole, to preserve the information of what it consumes, is forced to store it in this violent, energetic shroud at its boundary, a desperate measure to allow that information to eventually leak back out via the Hawking radiation. The existence of a firewall would completely reshape our understanding of these cosmic giants. A black hole would no longer be a simple, featureless pit in spacetime, but an object with a complex, highly structured, and incredibly energetic surface. It transforms the event horizon from a passive mathematical boundary into the most active and destructive place in the universe. The debate over this hypothesis is far from settled. Critics argue that the firewall creates its own paradox, violating the equivalence principle that is the foundation of general relativity. If you are in free fall, you should not be able to detect a local difference when you cross a gravitational boundary. A firewall is about as local and detectable a difference as you can get. The search for a middle ground continues with ideas like fuzzballs in string theory or other non-violent transfers of information. Yet, the firewall hypothesis stands as a powerful testament to the depths of our current confusion. It forces us to confront the possibility that the marriage of quantum theory and gravity is not a gentle union, but a turbulent and explosive one, and that the true nature of a black hole's edge is a hidden, high-energy frontier where the very laws of physics are forged in fire. Now, let's turn to a dark matter candidate so clever and elusive it seems to actively hide from our attempts to find it. This is the chameleon particle, a hypothetical entity whose very properties are not fixed but change depending on its surroundings. Just as a chameleon lizard alters its color to blend into the background, this particle adjusts its mass and interaction strength based on the local density of matter around it. In the deep emptiness of intergalactic space where matter is sparse, the chameleon would be incredibly light and interact extremely weakly. This would allow it to form the vast, diffuse halos that guide the motion of galaxies without collapsing into dense clumps. But here on Earth, in our matter-rich environment, the story would be completely different. Surrounded by the dense material of our planet and our laboratories, the chameleon particle would become heavy and its interactions would be suppressed, effectively causing it to hide in plain sight. This remarkable ability to shapeshift is not just a quirky feature. It's a direct solution to one of the most frustrating aspects of the dark matter hunt, why we haven't found it yet, despite decades of searching with incredibly sensitive equipment. The theoretical foundation for the chameleon is deeply tied to concepts of modified gravity and new fields that permeate space. It arises from models where a new, cosmic scale field interacts with ordinary matter, but in a way that creates a kind of shielding or screening mechanism. In a region of high density, like a planet or a star, the field is effectively screened. It becomes very short-ranged and massive, meaning it can't exert its influence over long distances and is very difficult to excite or detect. This is why, in your living room or deep inside a mountain laboratory, the chameleon field would be dormant and its particle counterpart would be elusive. But in the vacuum of space, where the density is incredibly low, the screening mechanism turns off. The field becomes long-ranged and the associated particle becomes extremely light, allowing it to mediate a new, long-range force that could mimic the effects of dark matter on galactic scales. This dual nature makes the chameleon a uniquely challenging target. The very experiments designed to find dark matter by looking for rare collisions in ultra-pure, shielded detectors are precisely the environments where a chameleon would be at its most shy and difficult to detect. So, physicists have had to devise entirely new kinds of experiments, moving away from massive underground vats of liquid and into the realm of exquisitely precise tabletop physics. These searches exploit the fact that even in a dense environment, the chameleon field cannot be perfectly screened everywhere. There should be a subtle residual force that extends a tiny distance into a vacuum. One of the most ingenious approaches involves using atoms as ultra-sensitive probes. In these experiments, scientists create an ultra-high vacuum chamber, a region of near-perfect emptiness. They then introduce a small, dense object like a solid sphere. According to the theory, the chameleon field should be strongly screened within the sphere, but just outside its surface in the vacuum, the field should change rapidly. This creates a force gradient. Researchers then delicately drop ultra-cold atoms near this dense object. As the atoms fall through this varying chameleon field, their quantum wave-like nature should be subtly altered. The path of the atoms would bend ever so slightly, or their internal energy levels would shift in a detectable way, revealing the gentle push of the hidden chameleon force. Another brilliant method looks for the chameleon's effect on light itself. Because the chameleon field can interact with photons, it could cause light to change its properties as it passes through a region where the field is varying. In a vacuum chamber with strong magnetic fields, scientists can search for a very slight rotation in the polarization of a laser beam, an effect that would signal that the photons are mixing with the chameleon field. These tabletop experiments are a beautiful complement to the colossal endeavors like the Large Hadron Collider. They represent a different philosophical approach. Rather than using immense energy to blast new particles into existence, they use incredible precision to listen for the faintest whispers of a field that permeates all of space, but has been hiding from us by masquerading as nothing at all. The hunt for the chameleon is a testament to the creativity of modern physics, demonstrating that if the universe is hiding its secrets in plain sight, we must learn to look not just with power but with unparalleled finesse. Now, let's consider a fascinating alternative to the classic WIMP scenario, one where dark matter is far from antisocial. Imagine a universe where the hidden particles don't just pass through each other like silent ghosts, but actually engage in a constant, vigorous dance of interactions. This is the world of SIMP, or strongly interacting massive particles. The name itself is a direct counterpoint to the weakly interacting massive particles we discussed earlier. Where WIMP are defined by their profound shyness, interacting only through gravity and the feeble weak force, SIMP are theorized to be quite the opposite within their own hidden sector. They could interact with each other via a new, relatively powerful force, a kind of dark, strong force that allows them to collide, scatter, and annihilate with much greater probability. This isn't just a minor tweak to the model, it fundamentally changes the story of how dark matter could have been created in the first moments of the cosmos. The classic WIMP narrative is known as the WIMP miracle. It suggests that in the hot, dense early universe, WIMP were created in particle collisions and then froze out as the cosmos expanded and cooled, leaving behind just the right relic density to explain dark matter today. It's an elegant story, but the persistent failure to detect WIMP has prompted physicists to explore other origin stories. The SIMP scenario offers a compelling and different plot. In this model, SIMP were not produced in a simple freeze-out. Instead, a process called number-changing interactions was crucial. Imagine a crowded, energetic party in the early universe filled with SIMP. In this hot plasma, 3 SIMP could collide and annihilate into 2 SIMP. This process effectively reduces the total number of particles while conserving energy. As the universe expanded and cooled, this rapid, self-annihilating dance had to slow down. The eventual relic abundance of SIMP we see today is determined not by how they interact with ordinary matter, but by the rate at which they cannibalize their own population through these number-changing interactions. This provides a completely different pathway to achieving the correct density of dark matter, one that is entirely driven by the hidden sector's own internal social life, completely independent of the standard model. This strong self-interaction isn't just a historical curiosity. It would leave dramatic and observable fingerprints on the present-day universe, particularly in the way galaxies and galaxy clusters are structured. One of the most significant challenges for the standard cold dark matter model is the core cusp problem we touched on earlier, where simulations predict dense central cusps in small galaxies that we don't observe. SIMP offer a natural and elegant solution. If dark matter particles are constantly bumping into each other, they behave less like a collection of individual bullets and more like a fluid. This fluid can flow and redistribute energy. In the dense central regions of a forming dwarf galaxy, these frequent self-interactions would transfer heat from the hotter outskirts into the cooler core. This process, much like stirring a cup of coffee, would puff up the central region, smoothing out the sharp density cusp into a much flatter, softer core, which is exactly what astronomers see when they measure the rotation curves of these faint galaxies. The evidence for this social behavior becomes even more spectacular when we look at the most massive structures in the universe, colliding galaxy clusters. We mention the bullet cluster as evidence for collisionless dark matter, but the story is more nuanced. While the bullet cluster shows dark matter sailing ahead of the slowed-down gas, other clusters, like Abell 5208, show a different picture where the dark matter appears to lag behind the galaxies. This is precisely the kind of signature SIMP could produce. In a colossal cluster collision, the dark matter halos from each cluster would slam into each other. If the dark matter particles are strongly interacting, they would experience a form of drag, not from the ordinary gas, but from each other. This would slow down the overall dark matter cloud, causing it to separate spatially from the stars, which simply pass through the collision unimpeded. This creates an observable offset, a clear signal that dark matter is not entirely collisionless, but has a rich and complex internal dynamics. The hunt for SIMP, therefore, shifts the experimental focus. While we still look for their potential annihilations into standard model particles in space, a major part of the search involves using the universe itself as a giant particle physics laboratory. Astronomers are now using powerful telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope to study the shapes of dark matter halos in immense detail, particularly in faint dwarf galaxies and in the aftermath of cluster collisions. By comparing the distribution of dark matter mapped through gravitational lensing with sophisticated computer simulations that include self-interactions, physicists can place tight constraints on how strongly dark matter can interact with itself. If the SIMP model is correct, these astronomical observations will eventually converge on a specific value for the interaction strength, revealing not just the presence of dark matter, but the fundamental rules that govern its hidden society. This transforms our image of the dark universe from a sea of isolated phantoms into a dynamic, interactive realm, a shadow cosmos with its own forces and relationships, forever hidden from our light but whose collective motions tell a story of constant, vigorous interaction. We have journeyed through a menagerie of hypothetical particles, from the ghostly WIMP to the wavy action and the social SIMP. But how is it that these wildly different entities could all be contenders for the same cosmic role? What fundamental process could allow them to persist in just the right amount to shape the entire universe? The answer lies not in the specific identity of the particle, but in the fiery conditions of the Big Bang itself. This brings us to a powerful and unifying cosmological narrative known as thermal relic dark matter. Imagine the universe not even a second after its birth, an unimaginably hot and dense plasma, a primordial soup where energy was so concentrated that particles were constantly colliding, annihilating, and being recreated from pure energy. In this frantic, seething chaos, any proposed dark matter particle, let's call it X, and its antiparticle, anti-X, were in a state of constant interaction. They were being produced from the collisions of other particles, and they were annihilating each other whenever they met. This state is known as thermal equilibrium. The particles and their annihilations were perfectly balanced, locked in a dynamic dance with the intense thermal bath of radiation. The density of these X-particles was entirely determined by the temperature of the universe, much like the density of steam in a boiling pot is set by the stove's heat. The key to this entire story is what happened next as the universe continued its relentless expansion. As space stretched, it also cooled. The average energy of the particles dropped, and the once packed cosmos became more diffused. This cooling had a dramatic effect on our X-particles. There came a critical moment when the temperature fell below the mass energy required to create a new X and anti-X pair from a collision. Suddenly, the process of particle creation from the background thermal bath effectively stopped. However, the reverse process annihilation could still continue. Any X-particle that met an anti-X would still mutually destroy themselves. For a brief period, annihilation reigned supreme, and the number of these particles plummeted. But then, another critical threshold was crossed. The universe expanded and diluted itself so much that the X-particles became too sparse to find each other. The average distance between them grew so vast that the probability of a meeting and annihilation became vanishingly small. At this point, the population of X-particles effectively froze out. Their numbers became fixed, a relic frozen in time from an era of incredible heat and density. These frozen fossils, this thermal relic, then simply drifted through the expanding cosmos, their abundance set in stone within the first fraction of a second of time. Their collective gravitational influence, dictated by that frozen in density, is precisely what we now identify as dark matter. This elegant thermal relic framework is what makes particles like WIMP such compelling candidates. The WIMP miracle is the stunning observation that if you take a particle with a mass and interaction strength roughly 100 to 1,000 times that of a proton, typical for a particle connected to the weak nuclear force, and run it through this freeze-out calculation, the resulting relic density miraculously matches the observed amount of dark matter in the universe almost exactly. It's a breathtaking coincidence that suggests we might be on the right track, that dark matter could be a natural byproduct of the universe's cooling, requiring no fine-tuning. But the beauty of this thermal history is its flexibility. It isn't exclusive to WIMP. Consider the action. Its story is slightly different, often called a misalignment mechanism, but it is still a relic from the early universe's thermal evolution. As the cosmos cooled, it underwent phase transitions similar to water freezing into ice. The action field is thought to have gotten stuck in a specific configuration during one of these transitions. As the universe continued to expand, this field began to oscillate throughout all of space, and the energy stored in those cosmos-wide oscillations behaves exactly like a super light, cold, dark matter particle. It's a different path to the same destination, a stable population of particles set in place by the cooling of the infant cosmos. Even the heavy sterile neutrinos from the seesaw mechanism fit into this grand narrative. They would have been produced thermally in the hot Big Bang. Being so immensely heavy, they would have been among the first particles to drop out of equilibrium and decay. But if they possessed just the right properties, their decay products could include the lighter, stable dark matter particles we detect gravitationally today. This thermal relic paradigm is the invisible backbone that connects so many of our seemingly disconnected theories. It tells us that we shouldn't be surprised to find dark matter everywhere. The process that created it was a fundamental and universal one, as basic as the expansion and cooling of space itself. The hunt for dark matter, then, is not just a search for a new particle, but a form of cosmic archaeology. We are trying to uncover a fossil record from the universe's very first moments, a relic whose properties are a direct message from that primordial soup, telling us what the laws of physics were like at energies we can only dream of recreating in a laboratory. After exploring the grand cosmological story of thermal relics, we arrive at the cutting edge of science where theory meets the formidable challenge of experiment. This final frontier is defined by a new generation of detectors and observatories, instruments of such breathtaking sensitivity that they are poised to either finally snare these cosmic phantoms or force us to completely rethink our approach. The quest is entering its most decisive phase, driven by projects that push the very limits of our technological imagination. In the deep underground laboratories dedicated to the hunt for WIMP, the next chapter is being written by experiments like LUX Zeppelin or LZ. Situated over a mile beneath the Black Hills of South Dakota, LZ represents a monumental leap in scale and precision. Imagine a massive titanium tank containing 7 tons of ultra-pure liquid xenon, chilled to -100 degrees Celsius. This vat of liquid becomes the target, and its extreme purity is crucial because any background noise could mask the faint signal of a passing WIMP. The core principle remains the same: wait for a WIMP to nudge a xenon nucleus. But when that rare event occurs, LZ is designed to see it with unprecedented clarity. The collision will produce 2 signals, a quick flash of scintillation light and a subsequent shower of electrons, creating a second pulse of light. By precisely measuring the timing and ratio of these 2 flashes, scientists can distinguish a potential WIMP interaction from the relentless background chatter of cosmic rays and natural radioactivity. LZ is so sensitive that it is probing regions of parameter space where these ghostly particles are theoretically most likely to exist, and its continued silence is itself a powerful result, systematically closing the door on the simplest and most popular WIMP models. Looking even further ahead, the vision for the ultimate WIMP hunter is embodied in the proposed Darwin Observatory. This is a collaboration that aims to construct a detector of almost unimaginable scale, a vessel holding 40 tons of liquid xenon. The sheer size of Darwin is not just for show, it's a fundamental requirement to catch the faintest whispers of interaction. With a target this large, the experiment would be sensitive not just to the recoil of a xenon nucleus from a WIMP, but also to a potential electron recoil. This dual capability allows it to search for other elusive candidates, such as the dark photons we discussed earlier, and even to perform unprecedented studies of neutrino physics. Darwin represents the culmination of decades of technological refinement, a machine that will essentially listen to the universe with such acute hearing that it will be able to detect the faintest footsteps of the hidden world, or tell us with great certainty that the WIMP we have long sought simply isn't there in the form we expected. Meanwhile, the parallel hunt for the ultra-light action is undergoing its own revolutionary leap with instruments like the International Action Observatory, or IOXO. While experiments like ADMS function like a super-sensitive radio receiver tuning for one specific station, IOXO is the next generation, a radio telescope dedicated entirely to the action. Its heart is a massive 10-meter-tall magnet producing a powerful, structured magnetic field. The core idea is the same brilliant conversion principle. In this magnetic field, actions from the sun or from the dark matter halo should transform into X-ray photons. IOXO breakthrough lies in its sophisticated X-ray focusing optics, akin to the mirrors in the Chandra X-ray Observatory, but designed specifically to gather these converted photons with incredible efficiency. This allows IOXO to scan a much wider range of possible action masses and coupling strengths with a sensitivity hundreds of times greater than any current experiment. It's not just looking for one station on the dial, it's rapidly scanning the entire cosmic radio band, listening for the specific frequency where the dark matter hum of the universe might finally break through the static. While these direct detection experiments listen patiently in the quiet darkness, particle colliders take the opposite approach, attempting to recreate the violent energies of the early universe to force these hidden particles into existence. The Large Hadron Collider has placed severe constraints on many theories, including supersymmetry, but the quest is far from over. The proposed Future Circular Collider, or FCC, represents a colossal ambition for the post-LHC era. Envisioned to be over 90 kilometers in circumference, buried deep beneath the European countryside, the FCC would smash protons together at energies nearly 7 times greater than the LHC. This immense power is not just for breaking records, it opens up a vast new territory for discovery. At these unprecedented energies, the FCC could directly produce heavy, hidden sector particles, including the elusive sterile neutrinos or even the partners predicted by supersymmetry, if they exist at these higher mass scales. Furthermore, it could probe the Higgs boson with microscopic precision, searching for those invisible decays through the Higgs portal that would signal the Higgs evaporating into the hidden sector. The FCC would be a microscope peering into a realm of physics we have only been able to theorize about, a machine capable of either discovering a whole new world of particles or compelling us to abandon some of our most cherished theoretical frameworks. Beyond our planet, a new eye on the cosmos is already providing a different kind of constraint on these theories. The James Webb Space Telescope, with its profound infrared sensitivity, is not a particle detector, but it is an unparalleled tool for mapping the gravitational effects of dark matter with finer detail than ever before. By observing the earliest galaxies and the most delicate cosmic structures, JWST is providing critical data on how dark matter behaves on small scales. Does it clump as predicted by the cold, collisionless model? Or do we see the smoothed-out cores and missing satellite galaxies that point toward fuzzy dark matter or self-interacting SIMP? The distribution and properties of the very first galaxies are a direct imprint of the nature of the dark matter that seeded them. JWST observations are already challenging our simulations, suggesting that early galaxies formed more quickly and are more abundant than some models predicted. This astronomical data acts as a crucial reality check, ruling out entire classes of dark matter models that cannot reproduce the universe we actually see taking shape in its infancy. Together, these endeavors the silent vigilance of LZ and Darwin, the precise tuning of IOXO, the raw power of the FCC, and the deep cosmic gaze of JWST form a multi-front war on the unknown. They represent humanity's collective ingenuity applied to one of the most profound puzzles of existence. We are no longer just theorizing, we are systematically probing the shadows, building machines that can listen for the quietest footsteps and look into the darkest corners of reality. The coming decades promise answers, whether they arrive as a definitive signal in a vat of liquid xenon, an unexpected particle in a collider's debris, or a revolutionary new picture of the cosmic dawn from a telescope orbiting 1,000,000 miles from Earth. The hunt has entered its most exciting chapter, where every null result sharpens the question and every new instrument brings us closer to the moment when the hidden universe is forced to reveal itself. From the ghostly reign of WIMP to the cosmic symphony of action waves, from the social dances of SIMP to the silent pull of entire mirror worlds, the sheer diversity of these theories is not a sign of confusion, but a testament to the vibrant creativity of the human mind when faced with the universe's greatest secrets. We have journeyed through a landscape where particles can be heavier than a bacterium or so light they behave as galaxy-sized quantum waves, where the fabric of space may hide tiny, curled-up dimensions, and where the Higgs boson could be a portal to an entire shadow universe. Each of these 30 ideas, from the established to the wildly speculative, represents a different path up the same immense mountain, a unique attempt to answer the most fundamental questions we can ask. What is the cosmos made of, and what are the true, underlying rules that govern its existence? This isn't just a technical puzzle for physicists in lab coats. It is a profound quest to understand the very nature of reality itself, to move from seeing a universe of stars and galaxies to comprehending the invisible architecture that makes it all possible. The fact that we can even conceive of such wonders, that we can build machines to listen for the faintest whispers from the Big Bang and telescopes to map the gravitational skeleton of the cosmos, is one of the great triumphs of our species. This ongoing search reminds us that our current picture of the world, for all its power and precision, is almost certainly incomplete. The anomalies, the tensions in the data, the sheer gravitational weight of the unknown, all point toward a deeper layer of physics waiting to be uncovered. The next great discovery might not come from a single eureka moment, but from the slow, patient accumulation of evidence that forces us to see the cosmos in a new light. It could be a tiny bump in a data plot from a deep underground detector, an unexpected pattern in the light of a distant quasar, or a particle that shouldn't be there appearing in a collider experiment. That breakthrough is out there, waiting for the right combination of theory, technology, and human ingenuity to bring it into focus. So, as we conclude this journey into the hidden particles of the universe, I want to leave you with a powerful call to stay curious. The story of our cosmos is still being written, and the next chapter could be revealed at any moment. Follow the news from these incredible experiments, from the James Webb Space Telescope to the next generation of particle colliders. Let yourself be amazed by the fact that we are living in an age where the fundamental laws of nature are being probed and potentially rewritten. The universe is far stranger and more wonderful than we ever imagined, and the greatest discoveries often lie just beyond the edge of our current understanding. I would love to hear which of these theories captured your imagination the most. Was it the elegant solution of the action, the mind-bending possibilities of the multiverse, or the stark simplicity of primordial black holes? Let me know your favorite in the comments below, and let's continue this conversation about the incredible hidden architecture of our